it's time to start. So I would like to welcome you to this Build System Hackathon week. And so I'm going to give a little overview of what we're going to do this week. So first, the objective of this week will be to understand how build systems work. So build systems, we will talk about CMake and GNU Autotools. And also another objective is to improve the way you distribute your software. So why do we want to do this? So the first reason is that if you go on a new system and you're not able to install your machine, you will be frustrated. Second reason is your users, because when they download software, if it doesn't work immediately, usually what they do, they go to find another package that's doing the same thing and that's easier to install. And in the case the users are not able to install your software, but they really need it, what they will do, they will send you tons of emails asking for help so that you will help them install your software. And you always have something better to do than to spend time installing software on an exotic machine for users. So if you do things properly, normally you shouldn't have too much about this interaction. Okay, and so the last point is that having well set up your build system, it will help you in everyday development. For example, when you want to make a release or something like that, it's going to be quite easy. So also I would like to mention that during the hands-on sessions, we give no support for the Windows operating system because it's quite different from Unix and Linux, and we don't have enough expertise among the helpers to support Windows. So at the beginning of the week, what we'll do first, we'll have some brief presentations of CMake. So CMake, it's Radovan Bast who is going to do it, and Autotools then by Christian Feld. And once you have these two presentations, it will help you decide which one is best for your project if you haven't already chosen one of the two. And then we will give longer tutorials on CMake and Autotools. So Radovan will also do the longer CMake tutorial this afternoon. And tomorrow morning, Evgeny Pozenitsky and me, we are going to make a longer tutorial on Autotools, so that at the end, you should be able really to choose which one you will take for your project during the week. Then in the middle of the week, so starting from tomorrow afternoon, you will work on your own code to improve your Makefile, to introduce or improve your build system. And at that time, there will be the helpers around that will answer questions so that you can show your code, ask for best practice, and so for asking questions and showing your code, we will use Zoom in breakout rooms. And if you have a question which is more general and where many people could be interested by the answer, it's good also if you post the question in the Slack so that everybody can see it. And during the hands-on sections, we didn't put any breaks or we just put some time where we will be available to answer questions, and then you can organize your time as you wish. So how to interact with us? So I said there was the Zoom with the breakout rooms. There is the chat, the Slack, and we will disable the Zoom chat so that we are sure that we have only one channel of communication, which will be the Slack. And I put here on the left the name of the helpers for this week. So at some time, some helpers will not be available. So for example, Radovan is going to be available, I think, tomorrow morning, but the helpers that will not be available on Zoom, they will keep an eye on Slack and they can answer questions remotely. And so we also ask you to do some participation to the hackathon. So we ask you to present your code at the beginning. to show how in what state it is right now. So how do you install it? Where do you download it? What are the problems you have? What you are not satisfied with? And so I wrote on this slide, don't be shy, because it's obviously it's not perfect, otherwise you would not attend this hackathon. So please show us what is good and what is bad in your code. So and share it with everybody, because it's maybe you have noticed some points on your code that are bad, and that others have the same problems and didn't yet notice it's bad. And so it's good if we are very honest about these code presentations. And then in the middle of the week, we will ask you also to present the progress you made during the hackathon, and also to take the time to tell all the other participants if you found on the web some useful information, if there are some tips and tricks, if you had some special recipes that you want to share with others. Then there will be a code swapping session. So each team will take the codes of other teams and will try to install it. And so the idea is that you can get some feedback from test users that will test your code on different operating systems. So if you have access to a supercomputer, you can try to install all the software on this one. If you have a Mac OS, you can try on Mac OS. If you have some uncommon Linux distribution, you can try also. So the idea is really to try the codes of others and give feedback. And during these presentations, so please don't spend too much time to make a nice PowerPoint or nice PDF. You can just show your screen. The idea is more a discussion, an informal discussion, to share some experience, more than trying to show that you have done a nice job. And also, if you have your progress is 0, it's interesting, because it means that something went wrong and that your problem is harder than expected. So don't be afraid to say, well, I had no progress, I'm still at the same point as the beginning, and the helpers will put more effort in helping you. And then at the end of the week, so you will be normally in a state where you will have done some progress with some build system that can help you install your software. And we'll have some presentations on what you can do now your software is properly building. So there will be one presentation on HPC containers with Kay Loening, Guix HPC with Ludovic Cortes, Conda, the packaging systems, Conda and SPAC from Leopold Taliers, and Todd Gamblin. And so that's it for my little introduction. So I would like to say that this hackathon is supported by the European Commission, by the TREX Center of Excellence. And also we had help from the EuroCC National Competence Center for the CMake part. And I would like to also thank all the invited speakers that allow this hackathon to exist. So does anybody have a question before we move on? So if you have a question, you can raise your hand, and I will try to see if somebody has a question. Yes. So Lionel, can you speak? Yes.
Yes. Yes. Thank you. Do we have your presentation and the other presentation somewhere?
Yes. Oh, yes. I didn't say this. So my screen is shared, so I can show you the Slack here. So in the Slack, you have here a presentations channel where we will put all the presentations. So here you have the Autotools PDF of Christian, who is going to talk right after. And Radovan is going to use a website to make his presentation. So you have the link here. And during the day, we will put them when the people are ready to share them with us. And also, maybe I can say a few words about the Slack. So there is a so when you will be in the hands-on sessions, depending on if you're working on Autotools or CMake, we recommend to use the proper channel so that everything is packed together with the same theme. If you have a general question or general information to share, it will be in the general. Any other question? No. Okay. Sorry, I see somebody else. Sorry, I'm not very good with this, so I need to find who it is. Yes, François.
Yes. Good morning. Can you hear me?
Yes, very good.
Perfect. Yeah, I have a question because I'm probably not going to work on my own code. I'm going to collaborate with the people working on Champ. So what would be the best way to proceed in this case? Because since I don't work on my own code, I don't really have anything to present.
Yes. So for the presentations will be by, for each team.
Okay. Okay.
Yes. So if multiple people want to present different aspects of what they, because if you share the work within the team, then you can present what you have done. You can say, well, my part was more this and that. But if you all work together on the exact same code, then one person can present.
Okay. Okay. Clear. Thanks.
Okay, so if there is no other questions, then we can move on to the first presentation by Christian Feld from the Jülich Supercomputing Center. So Christian, can you share your screen?
Yeah. So I'm just trying to, okay. So, okay, I think you can see my slide now.
You can see your slides.
Okay, great. So, yeah, how did I come to this hackathon? So some months ago, I saw an email on the AutoConf mailing list from Anthony asking for someone who would be able to give a presentation, Autotools, or even a tutorial. And well, I contacted him, and he persuaded me to give some talk about Autotools. And I was quite surprised that in 2021, people are interested in Autotools, as they don't have the best reputation. But I will give my best to tell you a little bit about Autotools and the pros and cons. So just a second here. Okay. I work in Jülich, and a cross-section tree performance analysis. There we develop some HPC targeted performance tools, so Scorpia and Scalaska, if you may know about, have already heard about that. And both of these tools and some others use Autotools based build systems since more than a decade now. And so our goal is always to run our software on every relevant HPC machine, or to build the software on every relevant HPC machines without forcing the user to do much fine tuning there. The tools here, Scorpia and Scalaska, they are also used in another center of excellence that might be interesting for you. It's a POP Center of Excellence, Performance Optimization and Productivity. So if you have an exascale ready code that you want to get a performance assessment for, also for free, just contact us. There is a link here at the bottom. So, and this might also be nice in a report, so that we show some collaboration between different centers of excellence. Okay, Autotools. So if you want to down or to install Autotools on your system, so there is no package called Autotools. So Autotools is a combination of 3 packages. So it's AutoConf, AutoMake, and libtool. And here I have some quotes from the Autotools book from John Calcote. It's quite recently, there was a second edition. If you really want to go the Autotools path, then I would recommend reading this book. So it helped me quite a lot. So AutoConf. So the first one of the three. So this is a tool used to generate this configure script that you probably know. So CMake, on the other hand, is a tool to generate some makefile templates from another makefile template that you have to provide. And libtool, the third one in a row. So this is supposed to provide a portable abstraction layer for creation of shared libraries, but this is one who causes most of the problems, I would say, especially in HPC. So if you just work with the GNU compiler, usually there are no big problems. But in HPC, we use different compilers and different systems, and their libtool quite often chokes. So the idea of using Autotools is to make the life simpler for the end user. So not for the maintainer. So you as a software maintainer or developer, you have to put quite some effort into creating a proper build system that will then be quite easy to use for an end user or for a packager. So the goal is also that if you have an Autotools-based build system, then it would be easy to just take your code tarball, put it onto another system, and build it there without any problems. This is often the case, but not always, especially if it comes to some weird HPC machines that are not supported, or where the compilers are not supported by Autotools. So AutoConf is available since quite some time, but you see here also a problem. So there was for 8 years there was no new release. So all these tools are not continuously maintained, which I see as a problem, especially here libtool. So the last release was 6 years ago, and just 2 weeks ago a new maintainer signed up. Probably there will be a new libtool release soon. And as a consequence, if you want to use Autotools and you are not happy with the released versions, then you have to patch the Autotools on the maintainer side. This is a pure maintainer job. And to provide then the generated files to your users. This is possible, but this is extra work, and especially patching libtool, this is no fun. So when it comes to documentation, I already mentioned this Autotools book. There's something online here, the Autotools Mythbuster. I haven't so much experience with this one. In addition, you have the reference documentation, but well, it's a reference documentation. It doesn't tell you the best practices and how to get started. Then there's also the Goat book. This is also available online, but this is quite outdated. I think it's from 2000 and an update from 2006. I won't recommend this for starting. Then there are also mailing lists for the tools. So there are not only one for each tool, but several. So you have a bug mailing list, you have a patches mailing list. So if you are interested in the Autotools, you should sign up for all these mailing lists. But yeah, there's not so much traffic there as, yeah, because the maintenance of Autotools is a little bit weak. I think people are turning away from it a little bit. What I'm going to talk about in the remaining is, so I want to show you how to build a very small Autotools project that installs a binary and a shared library. Then after that, we want to add a custom check for a library and a header. So this is at least what we do quite often for our software. And as a third part, I show you how to customize the distribution tarball and the installation. So for example, if you want to add some documentation into your tarball that is generated with some special tool only available on the maintainer's machine, and how to deal with this kind of situation. So all of that has the goal to make life easier for the user of the software. And then in the end, I have some pros and cons about using Autotools in HPC. Okay, when you use Autotools, you have two distinct roles that you should always have in mind. On the one hand, there's a project maintainer or the developer. His job is to make the life easy for users and packages, and also for other developers that don't maintain the build system. So the maintainer develops some configure checks, and these configure checks provide some conditional and substitutions that can be used in the source code and in the generated files. So this is basically the configure run. This creates conditionals and some variables that get substituted in the code or in the make file that is then executed. And the project maintainer also creates some release tarballs, and this is quite an easy task when you use Autotools. So the maintainer and also the developers, they work in a special environment, so they need Autotools, potentially patched versions of Autotools. They need M4, but this is usually always available on Linux systems, Perl as well, Shell, SED, and Org. So it's except of the Autotools or the specific version of Autotools, nothing special. The user or the packager on the other side, to make his or her life easy, she just downloads the package, so the tarball, it gets extracted. You create a build directory that can be outside of your of the downloaded code. You cd into this build directory. You run configure-help to see all the options you have, and then you just run configure with some options, and then just run a make all, potentially a make check if the package comes with some checks, install, and maybe also install checks. That should be it for the user and the packager, especially for the packager. So for example, for some Ubuntu or Debian packager, they rely on some stage installs. So this is already built in the Autotools infrastructure, and this should work out of the box if the maintainer created a functional release tarball. We will come to this later. So the user doesn't need to have the Autotools installed on his machine. There just needs to be a compiler and a shell and some basic Unix tools that are always available. So Anthony mentioned Mac OS and the Windows OS in his introduction. So the Autotools work on Mac OS because it's a Unix-based system. For Windows, You can use this MinGW environment, but I have not so much experience with it. And what I remember is that is extremely slow to work in this environment. There you rely then on the GCC compiler, if I remember correctly. Okay, so let's start with a first quite minimal project. So your project comes with some source files here. So my first program.c. Well, here I have a project just using C code, but Autotools also supports C++. And Fortran, for Fortran, you don't have the expected dependency tracking. So when you generate some Fortran modules, I know that there are some external tools that you can then somehow integrate into Autotools. I have no experience with this myself. For our software, we just have 2 or 3 Fortran files where we hand code the dependency into the make file. So modifying or hand coding, customizing this stuff is always possible, but usually you expect some automatic dependency tracking. This works out of the box for C and C++, not for Fortran. Keep this in mind if you think about moving to Autotools. So yeah, so this is basically your source code here. This foo is going to be a shared library that is also gets installed. So we also want to install this header here. And then here we have some documentation file that should be part of the distribution tarball. So now if you want to use Autotools to build your software, to install your software, to create a tarball, then you need to provide, as a maintainer, 3 files. We have first this bootstrap, but this is just a convenience wrapper. You can live without it, but I won't recommend this. Then you need to write a configure AC file. This is basically the file from which then the real configure script is generated, and a makefile.am. So this AM stands for automake, which is used to generate in the end the make file. In addition, we need some, or I recommend to have some special directories here where all intermediate or nearly all intermediate build system files reside. Okay, and basically all of this here then goes into your source code repository, and I think I switch now to my terminal here. Let's see. Okay. If the screen size is too small.
Yes, it's a bit small.
It's a little bit small, okay. Better now?
Yes.
Okay. Okay, so this is not the, just a second. So I want to go to the first version here. Okay, so here we have the files that can be seen here on the slide. And now we look at the individual files. So we first have this bootstrap. So this is just a convenience wrapper to call autoreconf. So AutoReconf can be the only tool that you need to interact with the Autotools. So usually, if you install the Autotools, you have 15 or 20 binaries installed on your system. But AutoReconf is the one which orchestrates calls to these individual tools. So you basically, this is quite complex and you don't want to learn it. Just do an autoconf -install, which installs all needed files into your working directory and warn about some issues, and don't recurse into some sub-projects. So we don't have sub-projects here, so just forget about it. And so you can also use a Bootstrap clean to remove all the generated intermediate files. These are quite a lot. So we can now do a Bootstrap clean. I think I did this, yeah, and now we have this basic setup here. So forget about Bootstrap. It's you provide it once and that's it. And then we have this configure AC file. So this is the file from which the configure script, which will be just a shell script, will be created. So this configure AC is a mix of some autoconf macros. So for example, you have here this AC init. This must be the first macro in your project. You give your project a name and a version. There can be more options, but we skip this for now. And at the end, you have this AC output, so which will then create some intermediate files that are necessary to run configure. Then here you have some helper scripts, or you tell the Autotools where to put some intermediate files. So here we had this build config directory and this build config M4 directory for this M4 scripts. So then we need a compiler. So, and here we can choose between the C compiler or the C++ compiler or the Fortran compiler. There's also a F77 for this old Fortran 77 stuff. I omitted this here. And for this example here, we just use the C compiler. So then we need to also initialize CMake. We can give it some options here, and I don't go into detail about these options. You can, yeah, this I think is quite well described in the reference documentation. We also want to make the make output less verbose, so we say to AutoMake, so generate some silent rules, so that you just see what's being compiled and not the actual compile command. But you can on the command line later switch back to the verbose mode, which is quite helpful to debug stuff. Some other call that is needed if you want to build shared libraries, but if it's not there, you get a warning when you run Bootstrap. So, and here this LT init, this is LT stands for libtool, and this initializes libtool with the defaults. That means you build shared libraries as well as static libraries. But by giving options here, you can decide what you want by default. The user can always override. Then here we have some generating macros. So here this AC config headers. This will generate config.h file, which is just a collection of some defines. So here, defines of previous configure checks will, or the results will be put here into this config.h file that then should be used as first include for every compilation unit that you use. And we also want to generate a make file in the end. So this is basically it for a simple project here. What needs to be in the configure AC file. The last file we need to take a look at is this make file. Here, the first line, we need to inform Automake where to find some intermediate M4 files. You write this once and then forget about it. And then here we have a variable, so bin underscore programs, and then here we have a lib underscore lt libraries. So these programs and this lt libraries that are called primaries, and this prefix here, this bin, this tells Autotools to install a program called my first proc into the bin subdirectory of the installation prefix. The primary LT libraries tells the Autotools to create a shared library and also create a libtool archive for it and install it in the lib subdirectory under your installation prefix. So these primaries are used to define the programs and the libraries you are going to install. So you can change. Yes.
Excuse me. I see a message. The font is very small. So can you make it bigger?
Too
again?
small.
Thank you.
Okay. Just a second. Oops. Okay, so yeah, so here this we are telling Autotools to create one program and to create one library. Those get installed. Then for the program and also for the library, we need some source files. So we take this name here and put it in as prefix for these variable sources here, and then here we list the C files and also the header files that should go into this program. Same here for the libraries. So we have this libfoo LA and then the sources, and here we list the sources that should go into this library. In addition, we can also provide some special flags, so preprocessor flags, the CPP flags, or this linker flags. And we can, at least for the programs, we can tell Autotools to link libraries into this program. So we do this by using this LD add. For libraries, this is also possible, but then the variable is called libadd. And here the line here include headers. That tells Autotools to install this foo header file from the library in the subdirectory include under your installation prefix. Then there's another special variable, it's called extra dist, that tells you that this documentation MD file should be part of your release table. So, okay, we have 3 files here, and I think this is also on the slides. Here we have the configure, here we have the make file, and here we have the bootstrap. And then we can actually execute the bootstrap and see what happens. So it's copying some files because we use the install option. And now we have quite more files than before. So we have this AC local, we have some temporary cache directory that we are not interested in. And here in our build config directory, we have some helper scripts. And in the M4 subdirectory, we have some M4 files that also contain autoconf macros. So here we have this config H. You might remember we had in the configure AC. Here we had this AC config headers, Bootstrap now created a config.h.in just because of this line here, and same for make file. So we had this make file am, and now we have a make file .in. So and these in files are now the templates when you want to run configure. So these files are then used to create your real config.h and make file once you run configure. Okay, let's do this. So here we are, in this directory here, we are in a completely different directory, so they don't know each other, but so Autotools are able to make out of place builds. So, but maybe just come back to this one here. So we also have, of course, this configure script here created from this configure AC file. So you start with just a few files. You run Bootstrap or AutoReconf, that creates quite some intermediate or some helper files. But the most important one is then the configure file that can be then executed, and this .in files that are needed by configure to create the real stuff. So now we can run this configure file, but first, this might be helpful for the user. We can do a configure --help. So this gives you the options that you can use configure with. So and without putting some special effort into this configure AC file, we just get quite some options here. And all of these options that are possible are described. So yeah, I won't go into detail here. You can specify where stuff gets installed. So this is usually not so important. You just provide a prefix where stuff gets installed and use the defaults. Here, for example, where is it? Okay, here you have this enable shared and enable static. So these are the options if you want to divide from the defaults that we have. So you see the default here is building static and building shared libraries. But if you want to change this, use these options. So there are quite some options, and I won't go into detail here now. So, but okay. So let's see. So there's something in this directory here. Before I do the first configure run, I just clean this directory. And now I do my first configure run. I just provide a prefix. So I want to install everything here in this directory, in the subdirectory install. And so I also could set a C compiler. So for example, GCC, but GCC is the default. So but if you want to divide from the default, just set the compiler like this. So we can run it. It makes quite some checks. And so I also won't go into these checks here, but let's see what's created here. So we see this config.h file here, and if we look into it, so we see here quite a lot of preprocessor defines that correspond to the checks made by the configure run. These are all built-in checks that we don't use in our code now. But if you add your own checks, which we'll see later, then these will show up here. Then we have this make file. This is the generated one, so I don't want to look at this make file in detail now. It can be quite lengthy. But now we are ready to just type make. So let's do this. And here you see the silent rules in action. You just see that CC is compiling some program and to the object files here, and the LD means we are linking something. So we are compiling the program, we compiling the library, we link the library, and then we link the programming. So now we can install the stuff, and we are still here in the maintainer world. So let's see what's getting installed. In our prefix here, you see we have this first program installed. We have this include for the library. So, and we have the library itself. So there's a static one, and there's a shared one, and some some symlinks. And we also see this libtool archive file here, which usually makes more headache than it's good for, but this is a default. It installs this LA files, and quite often you find some packages where these LA files are broken, and then this causes your build system to be broken as well. So therefore, quite a lot of Linux distributions just delete all this installed LA files. Okay, so that's basically it for a very first. No, it's not. We're not ready yet. So we are here in the maintainer role, and the job of the maintainer is to provide a tarball to the user. So far we just did some little development here, and we we did a make. We can also do a make check, for example, but we haven't defined something here. But this would also be a job of the maintainer or developer. But to create a tarball for the user, there is also another target in the make file. So by the way, the make files generated by Autotools, they comply to the GNU coding standard. So there are quite some targets in there that packages expect to be there. So if it comes to packaging, so everything is taken care of by Autotools. You don't have to deal with it. But so to create a distribution tarball and also to check it after it has been created, there we have this check rule. So it creates a tarball, it unpacks the tarball, it runs configure in a special environment. It runs then make, make check, make install, check, make uninstall, and everything is as expected. It tells you that the distribution tarball is ready. Okay, so this is went as expected. So we have now a distribution tarball that you can happily ship to your users, and that is expected to run on every, or to be successfully compiled and installed on nearly every Linux system, with quite a lot of compilers that you specify at configure time. So if we look into this tarball, so we see the generated files that we also saw here in the maintainer mode. We see our source code, we see the generated configure here, and we see the generated config.h.in and also the makefile.in. So with this tarball, a user just needs a compiler, some shell tools to build this tarball on his or her machine. So no need to have the Autotools installed on the user side. Okay, this was a very first project, and I'm running out of time already. So a little bit of this stuff is on the slide. So this is my first Autotools presentation, so not everything is quite polished. But so we haven't put in a special check for our own code. We first just compiled a few C files, and that's it. But if you are working on a real project, you need to add more to your configure AC file. And there are 3 macros that are quite important and that are used quite often. So this is the AC subst. This substitutes some variable in your configure AC file to this .in files. So for example, in this makefile.in, there are lots of these variable add, and this then gets replaced by the values you pass to AC subst. If you need some more defines in your config.h file, you just use the AC define, and there are some options, AC define unquoted, and I think there are some more that can be looked up in the reference documentation. This macro then adds defines to your config.h file. Also quite important is this AM conditional. This allows you to do some conditional compilation into your makefile AM. Let's see how this can be applied to our project here. Also be aware that there are, before you write your own macro, there is a macro archive where you can download well-tested macros that might be useful for you. So what I wanted to show here, but I just have a few minutes left. Maybe I can continue tomorrow when there is this this hands-on, if you're interested in. So I wanted to check how to check for an external library that is needed for your program. So imagine that your program needs to link against the PAPI library. This is a library to access hardware counters. It would need two more source files, so the mypapi.c and mypapi.h, and we want to write a special check at configure time, and also to allow the user to select this PAPI feature or to deselect it, and to point configure to the right location of the PAPI library, because on HPC systems you usually don't want to pick up just the libraries that are installed in user lib or user local lib or everything ld-config files, but quite often you have a single directory for a single library in a single version. So therefore, it might be useful, so it depends, to create your own own check for a library. And you define an own check or an macro with this ACDFun variable. And yeah, I marked in blue some of the macros that are used quite often. So this is a combination of some autoconf or M4 macros together with some shellcode. Here, for example, we have just some shellcode. Be aware that this shellcode should also be written in a portable way. So some of the test constructs, for example, are not portable. There's an entire section of it in the autoconf reference documentation. But in the end, we define some output from the macro, so I don't have time to go over it here. We define an automake conditional. So if PAPI is available, and we also define a C preprocessor define with the same name, and we do this substitution 3 times. So for the library, for the CPP flags, and for the LD flags. Here, I'd like to mention the -R, which is also important, I think, on HPC systems. This -R, in addition to the -L, which is quite common, this adds some R passing flags to the link command. So even if this PAPI libdir is not automatically found by your runtime linker, with this -R, it's hard coded into the binary. Okay. Yeah. So there are some. These are the changes you need in the configure file, configure AC file, in the make file AM. So yeah, here you just use this variables we AC substat in the configure AC, or in this special macro, and here we use this automake conditional. So if we have PAPI, we do this stuff. If we don't have PAPI, we want to have this files here in the distribution. Otherwise, so this here puts them automatically into the distribution. But if configure doesn't find libpapi, then you need to do some extra work here. In the C files, you can then use the defines like this. This is, I think, straightforward, and they come from this config.h here. So you are supposed to include this at the very beginning of your compilation units. Okay, then there's another part that I skip in total. So this was about how to customize your installation and the distribution table. So just some some wrap up here, or some experiences that I made with Autotools. So they are extremely flexible. In the end, it's just a portable shell code and Makefiles. So you can do everything in your Makefiles. You can also, or in the Makefile AM, you can write your own targets. You can customize the installation and the distribution, and you can basically do everything with these M4 macros. Really, so if there's a problem, you can somehow figure it out. But yeah, it's quite some work. Also, this make disk check, I think, is extremely helpful to get the contents of your tarball right. So your user or the packager will be happy when you provide a tarball that survived make disk check. The configure dash help I also think is quite useful. So for the user, you see how to configure your package and what's in there, what features can be activated or deactivated. So there's the make is parallel. So, and you have this out of place build. So also make speed is not of such an issue. Configure can be quite slow. So, and you have just minimal requirements on the user system. There are also some cons, and there are more cons. I think the learning curve for Autotools is quite high. So the online beginner's guide on the web, I'm not so satisfied with, especially in the context of HPC. To learn this is quite time consuming, and yeah, you should really expect some frustration. So debugging is quite difficult. So you basically have to compare some generated files using diff or some diff tool. This quoting you saw, this M4 quoting with the brackets, this, yeah, there will be surprises, and I really recommend to do some very fine-grained changes, check if everything works, and then go on. If you write 50 lines of M4 stuff, it's really hard to find the place where you forgot a bracket or something else, and it, yeah, fails then on places where you don't expect it. Yeah, also the what I really see as a problem in the long run is that the tools are not continuously maintained. So, and that they are not aware of all HPC relevant compilers. So we, for example, for our tools, we have to patch autoconf and libtool. We have more than 10 patches for each of the projects to get them working on the machines that we like to support. So for example, you have this gray machines that need to have some special attentions. You need to have this Fujitsu machines. Then NVIDIA now has this NVHPC compilers that was previously the PGI compilers. So there you have to add something to libtool. That's not in there in the real distribution, and it's yeah, usually patching libtool is a pain. Then so I didn't show you this AC checklib, which is a macro that you use maybe quite often if you rely on external libraries. That doesn't use libtool during configure, but during make you use libtool, which depending on the LA files and if you have static or shared libraries will be surprising. Yeah, so I already mentioned this libtool archive files that are sometimes broken. They refer to files in the build directory and not in the install directory. It prevents sometimes the mixing of compilers of the library and the binary. And so usually I would recommend to just get rid of this LA files. Yeah, libtool decides on compiler names. sometimes. And so then in addition, special handling is needed for compiler wrappers. So MPICC and HPC, I think is more common than just GCC or ICC. If there's no support for this special compiler wrappers for the special vendor of the compiler, then you don't get position independent code, and you need to patch lib2. Yeah, so on lib, I mentioned the problems on Cray systems, so there are some workarounds available if you know the Cray employee that invented them. So yeah, if you just use some GNU compilers, usually the world is as expected. So you create a tarball and it runs on lots of different systems. In HPC, you need to expect some issues. You can work around all these issues, but this is quite some amount of work. And yeah, writing this additional configure checks and dealing with this not so straightforward setup of Autotools might not be fun. So there's no built-in dependency management for Fortran, which I think is you shouldn't consider using Fortran with Autotools, my personal opinion, but it's okay for C and C++. Yeah, that's basically it from my side for this very brief introduction. So there's a lot to learn. You can do quite a lot of stuff, and in the end it feels quite cool if you achieved something, but I'm not sure if this the time you need to put into Autotools is a well spent time. So we have it and we have to live with it, and if you have a project that already uses Autotools, I think it's hardly justified to move to something else. Well, it depends on the funding you have. But yeah, so I can't really fully recommend it for new projects. So if I would have to start our projects again, I would first do quite some research and look at alternatives that I think we will learn in the next we'll learn about in the next talk. So, so do you have any questions now?
Hello, can you hear me?
Yes.
Yes, first of all, thank you for your presentation. I would like to ask if it would be possible to share those examples you are showing to us, because for me sometimes it would be nice to look at some files for a little bit longer.
Yeah. Okay. So I have it in a local Git repository. I try to upload it to some publicly available server.
That would be nice. That would be nice.
Yeah, and I will put it then in this Slack channel here in the Autotools section.
And
yeah.
Okay, thank you. And the second question I have is about this Fortran dependency management, because as far as I know, I work with a couple codes that use Autotools, and they were basically written in Fortran. Correct me if I'm wrong, but I think Quantum Espresso is uses Autotools, and it's written in Fortran. So my question is how to fix this auto dependency management check.
The dependency management is used for, so you change a header file and all the relevant all the C files that consume the header file are rebuilt. And in Fortran you have this modules, and if you change the module, then all the consumers of the modules need to be rebuilt. And to my knowledge, there is no automatic way to do this. You can do this manually. So I found something on Stack Overflow, but this is then a manual approach. If you are in the user role, so you just download the tarball and install it. So there is no need for this dependency tracking. So dependency tracking is useful for a developer who constantly changes the code. You could also always do a complete recompile, but this is quite time consuming.
Yes.
So I know that there are some third-party tools that can help you in with this dependency management in Fortran, but I don't know how to integrate them into Autotools. So I've basically, I'm not a Fortran developer, so I just have very minimal exposure, but this is what I heard so far. So there might be some third-party tool that might help you, but you need to figure it out yourself.
Yes, thank you very much. Yes, the module files in Fortran are quite annoying, and basically on my projects, I most of the time have to use make clean all the time because
that's a workaround.
Yes.
The time-consuming workaround. Yeah.
Yes, but the thing is, just recently I was working with some Fortran parsers for the completely different project, and then I realized they can be very easily used in such a way just for these checks. Basically, it would introduce a dependency for Python and these libraries, but to get the dependency tree from them is like 3 lines of code. So maybe that could be an option, but just my recent experience, just recent idea that I had a few days ago.
Yeah.
Okay.
Yeah. So this, as I said, you can do or you can extend the Autotools as you like. So in the end, it's just shell script and some make targets. And so if you find a tool that helps you then with Fortran, then yeah, this would be the way to go. But you have to do it yourself. So there's no built-in way to do this. Yeah.
Okay. Thank you very much.
You're welcome.
So there are also 3 other questions.
Yeah. Okay.
So Nick Rubner, Papier has a question.
Yes. So you basically said that one shouldn't go into Autotools and that probably CMake is better. But what about other build systems such as Vison or something like that? Could you?
Yeah, I've no experience with Vison. I think most of the build systems are a pain for the build system maintainer. So I know from our easy build maintainers, so and on our in Jülich, so they quite often complain about CMake. I don't know why. So I think it usually you can build with every system, you can build some cool tarballs or some cool packages, but it's very time consuming to get this right, and not to only get this right on your machine, but to get it right on real HPC machines. So what we do, so we test on all the relevant machines when we have a new push to our project, and we also have an Autotools playground project just to test new new macros that we write on all the for us relevant HPC machines. So this is quite some effort we put into this build system thing. I'm not sure if it would be much less effort if we would use CMake, but for us, this is no option because we have no funding to switch to something different, and we put quite some effort in our system, and it works quite well. So yeah, so but in HPC, I think you you need to invest quite a lot, and I think it's no different. Or yeah, you need to invest a lot in Autotools, and you need to invest in CMake, and you need to invest in other build systems if you want to get really portable build systems, and you should really test early on all the relevant systems, and you will be surprised what can go wrong.
Thanks.
You're welcome.
Anthony, you're muted.
Yes, sorry, I was saying that Lionel Ilgues has a question.
Yes, is there a relation between Autotools and PKG config? Is it common practice to use the two together?
The package config, I think, provides an M4 macro that can be used with Autotools. So we don't do this, but it can be done. So there is a, I don't remember the name, but there is a macro coming with package config that can be used to easily access the values that package config provides. Yeah.
So I can add that tomorrow we will show you how to use package config with Autotools.
Okay, thank you.
And so I also have a question, because so you in your last slide you showed that there was a problem with libtool and Cray systems, and I'm somewhat very surprised because there are so many packages using Autotools that I don't understand why a vendor like Cray doesn't patch himself the libtool, because otherwise you need to ask to all the package managers of everything in Linux to change.
It's on the Cray systems, it's a problem with proc and Cray, so just the Cray compiler. And the Cray employee sent a patch to the libtool mailing list some years ago, and he just was ignored. So this is a problem of the maintenance of libtool. So yeah, the thing is that you as a maintainer, you need, if you want to support all these HPC systems, you need patched versions of Autotools. Otherwise, it just won't work with the MPI compiler wrappers. It just doesn't work. It works with GNU and Intel, but not with the IBM compilers, not with the NVIDIA compilers, not with the old PGI ones, not with the Fujitsu ones. So we build everything, or we patch our tools, and we need to use these patched versions to create the tarball that then runs on all the systems. Yeah. So if someone gets our source code and rebuilds all this stuff, or does this bootstrap again with his versions, so usually this would fail first because he has to use the same versions we use. So we use a little bit outdated version of CMake. So this would be the first problem. And then all the patches that we put into libtool would get lost. So yeah, so on the maintainer side, or all the developers, should use a special version of the environment. So special version of Autotools with all the patches available. Then they can do the tarball using make dist or dist check that then works on every system that are currently under our automatic testing.
So then it would be a good idea to make a repository for patch clip tool so that everybody can benefit from this.
Yeah, so usually we try to get the patches into libtool or autoconf, but as the maintenance is well questionable, they are just flying around on the patches mailing list. So yeah, so we have our own repositories, and if there's someone interested, we can think of sharing it, or you can yeah, somehow we can come together. At the moment, they are not publicly available, but this would be one of our next steps. Yeah.
Okay. Thank you.
Yeah, welcome.
Okay, so now it's 20 past 10, so I propose that we have a little break, a 15 minutes break, and then come back at 10:35 for Radovan's presentation of CMake. So I will display just a timer so that we see how much time is left for the break.
Anthony, we can see your screen.
Thank you. I forgot. Okay, welcome back. So it's 10:35, and so we can move on to the presentation of Radovan Bast from the University of Norway.
Thanks. Yeah. Hi, everybody. Let me know if audio is somehow strange, and I will adjust. And hi from Northern Norway, Tromsø. I don't know if my camera resolves it, but out of the window you see that we got a lot of snow. So hello from winter. Would be actually fun to see where everybody else is. Maybe we can share later on like social channel, and it's like where people are and how the weather is. So let me take the screen and I will tell you a little bit. So we will talk about CMake. Just a quick adjustment here. Screen, I will adjust. And I know it's still not great, and I know the font is too small. But maybe first note is that the zoom window is now like portrait and not landscape. And the idea is, so you might need to readjust on your side. But the idea is that later when I do something in the terminal, I will switch to the terminal and I can switch here to the material. And the idea is that you have half of your screen free to do something else. For instance, you could browse the material, or you could try some of these things out in your terminal. So if this doesn't work well, then I can change on my side. But this is something that we have seen works well in other workshops. So we can try it out. Now, I know so I think the link to this you find in the Slack. There is a lot going on the website, but there is stuff for the afternoon. So in the afternoon, we will go to the tutorial, and many things here are for the tutorial. So now in the morning, I will talk half an hour about CMake, and I will only look at this top left motivation and overview, and I will zoom in. So I know that this is not really readable. So I'll talk about motivation and overview. We will also try some of these things out, just to see what are the things that CMake really shines at and what are the problems. Also, one clarification is that you see here copyright EuroCC, ECCNCS. No, how is it? No, sorry, it's called ENCCS. And I just want to clarify that I'm not affiliated with them. I have friends working at the ENCCS Sweden, but I'm not related. I took the material, so this material is based on their workshop, but I have changed many things here. So many things have changed, which means that if you see something that doesn't work well, let's not blame it on ENCCS. That's my fault. All right. So I will now go into the motivation overview, and I will zoom in. So the sidebar will disappear, and you can also follow along, and you can try to browse a bit. And so there is two more things I wanted to say. One is that I really like the format. So thanks for inviting me to speak here and to be part of this. How did I get into this? So I know Anthony and Evgeny and Vijay from other contexts. I've also worked a long time ago in Toulouse. So I was really excited to participate here. And I also really like this setup that I like this idea of swapping codes. That's really great. Also that we are really honest about things that are great, but also things that are not great. I have written a lot of CMake code which was not great, but I think this is really the point here, that we share our lessons learned. It's not about showing only the perfect stuff. So let me start here, motivating CMake, what it is, and now the goal is that we get a taste. We get a bit of a feel for what it is good for, and what it is maybe where the problems are. And I think it's good to take a step back and first think about, okay, so why do we have this workshop? Why don't we just build everything with Make? And actually we do. I think most of the software that is compiled, maybe I'm wrong, and I would be actually interesting to hear if somebody here is actually building software not with Make. because it doesn't matter so much whether we use EasyBuild, Spark, CMake, Autotools. At the end of the day, very often it's Make. Not always, but very often. But it's not enough, because Make is really good at doing what we tell it to, and we tell Make what depends on what. But it doesn't know which compiler we want. It doesn't know which environment we are on. So discovering the environment, telling Make what compiler flags. It doesn't know about Fortran 90 order of. We need to tell it in which order it should build the modules, and then it will do it. Which means that in any project, you often start with a Make file, but then you realize that it's not enough, and then people either go to Autotools or they write their own scripts. And I have grown up in a project where we wrote our own scripts, but then it didn't work. So I came into CMake in 2008, and a colleague came into the office, showed me CMake, and then that was the moment when really I was absolutely amazed. I was stunned. Hopefully I can give you some of this excitement here. And that day I actually deleted this manual configure script that I was working on for a couple of weeks, because I understood that this is not the way forward. So I switched to CMake. I spent like a decade writing CMake and in Fortran, C, C++. In the last 2-3 years, personally, I do most of my coding in Python and Rust, but I still really appreciate CMake. I still think this is a great tool. I still maintain Fortran and C and C++ code. So let's talk about CMake. What is it? What it is not? CMake is cross-platform. So the C in CMake stands for cross-platform. It doesn't stand for the C language. So that's one possible misunderstanding. The second one, it's not a replacement for Make. It's maybe an alternative to Autotools. It is open source. It's very actively developed. It is written in C++. It doesn't matter. It only matters if you really want to actually compile CMake, but you almost never have to, because they really ship to all the different distributions. But it's good to look at this picture. So we have on the left side, I have these different source files, C++, C, Fortran 90. And very often we compile them with Make. So there is a Make file involved. But what CMake does, CMake actually generates the Make file. So based on some recipes, and we will create files called cmakelists.txt. There is typically one or several such files. And then CMake will go into these files, it will figure out what we want, and it will generate the Make file. But then I built the project actually with Make. But it will generate a Make file that is very often sort of perfect. It has the right dependencies. You can build on 32 cores in parallel if you want to. And my tutorial in the afternoon will be really about how can we write this cmakelists.txt. So it is a generator. CMake is not a replacement for Makefile. And in fact, Makefile is not the only one. So one thing that I can try in my terminal is to type cmake.help. And there is a lot of help output, but it lists the different generators that are now available on my system. And Unix Makefile is only one of them. There is Ninja, and there are some other ones, Eclipse, and some of them I don't even know. So it can generate project files for any of these. I think in the research software and high performance computing setting, we very often are interested in generating these ones. I will just move so that I can also see the chat if there is anything. So it can generate any of these. It offers a complete toolchain So here is a picture which might be a little bit overwhelming, but I will walk you through it. So most of the time when we start with a project, and I think this is also maybe our ambition for today and this week, for those of you who start with CMake, is that we are in the gray box here above. We have source files, Fortran C++, and then we will create this CMake list.txt, one or several. And based on this, most of the time we will only want to build targets, executables or libraries. On this graph here, I show that CMake can actually do much, much more. Some of the things we will explore in the tutorial, some of the things we will not, because they don't fit, but I just wanted you to know about them. So CMake can actually generate source files. It can generate source files at configure time or at build time. It can create packages, source packages, binary packages that can be installed. What we very often want to do, as I said, is we want to build our libraries and binaries, and then we want to test them. So CMake also has a test framework. It even has a dashboard where you can then display nightly tests, weekly tests, and it can also do all this make installing. So there is a lot of possibilities. We will look at some of those. So why would one want to go to CMake and not to any of the other, like Autotools, and there Meson was mentioned, and there's Bazel and Escons. And maybe I can plug in a quote. So paraphrasing Bjarne Ståstrup, I think the build tool that nobody complains about is the build tool that nobody is using. So I mean, you will always find there will be complaints that can be made about CMake as well, but CMake shines in a couple of points. One thing that we will see in the little exploration that I will start in a moment is that we have out of source compilation. So we always build a project, all the object files and the library files and the binaries and everything we generate it outside of the source tree. We create a new folder and everything goes into there. So you don't really like pollute your folders with object files. And the nice thing about that is that we have the possibility to compile several builds with the same source code without copying the source code. This is wonderful for development. It is really cross-platform. In our context, very often we are mostly interested in Linux for high-performance computing reasons, but CMake will build on Linux, macOS, Windows, also on the other things which I didn't try out. Well, I did try AIX a long time ago. It knows about the system, so you don't have to write scripts that then discover the operating system and versions. It can do this discovery of system, but also library discovery. We will see that. It has excellent support for Fortran C++ and Java, although I admit that I have never tried Java. It can do mixed language projects. And what I really like is that Fortran is a first-class citizen here. So Fortran is not an afterthought, Fortran 90. The support for Fortran and Fortran 90 is really excellent. This was a nice surprise because I was kind of used as a Fortran developer. Back then, I was really used that tools are always a little bit worse for Fortran than for C and C++. And this is not the case here. I will show you that CMake understands Fortran 90 dependencies very well. You don't need to plug in a third-party scanner. You don't need to program your own. Also, excellent support for multi-component, multi-library projects. So as projects, as they grow, then you like to split them up into libraries and components. And CMake is really good at stitching this together and keeping this, having the possibility of having modular projects. Oh yeah, here I have it. Support for modular code development. So you can include external modules, which are maybe sitting on a different Git repository, and CMake can orchestrate all of this. It provides a couple of tools out of the box, like a user interface, a command line user interface, even a graphical user interface. There is a testing and packaging framework. I will, in the tutorial, show CTest. We will not look at CPack, but CPack can generate like Debian packages and RPM. We will see that CTest, the testing framework, is wonderful because it allows us to run sequential tests in parallel. That's really super. And it is used by many projects, especially now. I see it all over the place. So I think it's good to, even if you decide to go for some other tool, I think it's good to at least know what's going on, because it's likely that you, sooner or later, you have to build a project that is in CMake, and then it's good to know where to poke into the code if you want to change something. I have mentioned that this is not bound for makefiles, although I will, on my computer, I will actually then go through makefiles. But I would love to hear if somebody here is building their code not with something else. Would be interesting to hear. There is a big community. Many solutions already exist. Like whatever you want to do, somebody has already done it on GitHub. I just want to browse here the list of the officially shipped. So these are the officially shipped modules in CMake. And I will just scroll here down because I want to show you that. Zooming in. There are all these modules for find Armadillo, find CUDA, find BLAS, LAPACK, all of these things that we need. Somebody has already written it to discover packages, to link them to. So all of this is probably already there. It is also, it can coexist with other tools because it's kind of non-intrusive. All you need is this file called cmakelist.txt. So it can be a nice way to sneak in a CMake build system into your project without upsetting everybody else, because it can be there and coexist with something else until people get used to it. All right, soon I will actually show you something in the terminal. Just want to summarize here. It is a domain-specific language. So CMake is a language. You can define variables, and you can loop, and you have flow control. There are if statements and options and command line interface, and you can use modules and includes and functions macros. So you can do everything. Let's have a look at the commands just for fun. So there are all these many commands that you can do, which is great, but also you can really implement everything you want. But of course, the language will also not prevent me from creating some very Byzantine, complicated contraptions. In the tutorial and workshop, we will revisit some of the good solutions and less good solutions. So what problems to expect when moving to CMake? CMake has many good defaults, and most of the time it just works, and it can feel a little bit magic. So that's great. I think problem comes when things don't work anymore. This will not happen very often, but it will happen at some point. Something doesn't work, and then it's good to know where do you need to go in, what do you need to print, how can you tweak things. This can be a bit, of course, it's a new tool. So the language and the module ecosystem offers all the possibilities, and it is easy to go a little bit overboard. So with more CMake code complexity, one can then compromise some of the portability. So CMake is portable, but it will not prevent me from creating solutions that may be less portable. And for larger development teams, it's a new tool. And I have now been in a couple of projects in computation chemistry and in oceanography where we have migrated to CMake. And I mean, there has been friction because it's a nice tool. And I would say it's the better tool compared to what was there before, but it's a new tool compared to the familiar tool that everybody understands. So there's always this technical aspect, but there's also this organizational aspect when moving to a different tool. Okay, I just need to, so I saw somewhere a notification that a hand was raised. I'm happy to take questions now before moving on. We can also wait until later. I don't know.
Yes, just a small question. I didn't get what you meant by overboard. What do you mean when you said it's easy to go overboard?
Yeah, that since I have all these possibilities in my hand, I can implement some very elaborate. I can program anything I want. I mean, I could program like a computer game in CMake. And I have already implemented some solutions which were just too complicated, too complex. It was unnecessary because I maybe programmed something that was already available in a much simpler way. So what I meant by that is that sometimes you have people complaining about CMake. CMake is too complicated, but it's sometimes not CMake itself. It's the code implemented in CMake that is complicated. Like in any other programming language. I mean, I can write unmaintainable code in Python or in any other language. So I have seen this happening, and I have sinned myself that I programmed something that was just too complex and unnecessary complex, just because it was possible, and just because I got excited about the possibilities. All right, we have like 10, maximum 15 minutes left. I wanted to give you a demo so that you can really, that we see some of it. And now it's not, the goal is not remembering any of the commands, because we will come back to that in the tutorial. But I just want to give you a tour, and I will go to this example here, brief tour, to demonstrate some of the concepts. And I think I want to show you maybe two, three concepts where it shines. You can find the example that I will build here. You can find it in this GitHub repository. Oh yeah, and I didn't even say why is this under this code refinery URL. So that's this project that I'm working on, where we teach researchers tools and practices. And I'm also happy to see that my colleague Johan is here also in the call. So you can clone or download this example. You can go in. Maybe you can try it later. I think at this moment I recommend to just sort of sit back and watch, but up to you. I have cloned this example here. Oop. Here I have it. I will go in, content examples, and it's the so the example here, it's a calculator. It's a silly code that can add and subtract. So we have there is some Fortran code in here. There is also some C code, so it's mixed. CMake doesn't mind. There is some source code, and also we will have some tests. And let me show you. So this CMake list here will tell CMake what to do. I have actually a couple of them here, and the motivation why I have several and not just one, I think this will come in the tutorial. It makes for a bit more maintainable code, but I could just throw everything in one file. And maybe we can have a look at the CMake list file. So I describe what CMake version do I need. This is a project with a name, certain version, and I tell CMake which languages I wanted to support, C++ and Fortran. This part here makes sure that I get a C++ 11 standard, because I just wanted to show you how to do that. This part here will make sure that when I later make install, things will end up in the standard places. The project would build just fine without any of this. So I could also leave it out. This is just as a demo. And then what do I do here? I actually refer to, so there is a folder called SRC, and I tell CMake to process another CMake list in there, so I can kind of modularize my project. And for the moment, so there is also some testing going on. For the moment, I will deactivate the testing. We will start just with the building. And And now I will build the project. And there are at least 2 ways to do that. In CMake, as I told you, the really important concept is that we build out of source. So I tell CMake where is the source code and where do I want to build into. So this can be any place, this can be any other place. Here I will configure, and here I will build. This is the better way, but actually this is not the way that I use, just because I do this all the time. And just because it's in my muscle memory. I have done this like 400,000 times, and I have done this maybe 30 times. So you will probably see me doing this. And this works well if you want to build with makefiles. This is more general because this doesn't mind. It can be any other build or framework. So more about that in the afternoon. But I create so I will create in CMake. What I often do is I create a build folder. I go in, it's empty, and then I point CMake at the location where is the CMake list.txt, and here it's 1 level up. So this will configure the project, and it detected some compilers. And in the tutorial, I will then show you how you can change the compiler, how you can tweak all of these things. And now in this build folder, it generated for me a couple of files. So all of this stuff is now generated. It also generated a makefile. I don't have to look at the makefile. I never go in and edit it. I could if I wanted to, but now I just want to build it. And now it built this project for me. There is an executable which I can run, and it does some calculation. One thing that is really exciting that I will hopefully show you is I managed to get the Git hash version into the output. This is really nice for reproducibility. So here I did something at configure time. I figured out the Git version. So I can do some things. I can generate source code at configure time if I want to, or at build time. So that's what we did here. What did I want to show you? So we ran the binary. Yeah, I showed you the main CMake list. I didn't show you yet the one in SRC. Let's have a look. And this is now how. Oops. Okay, I understand that this is a bit out of the window. Here we don't need to know any details, but I just wanted you to see how a CMake looks. So I defined some libraries. I built a library out of some source code, and then we define where are the include folders. I define an executable, and I link the executable against the library. This stuff down here will tell, if I do make install, it will tell where to put the places into. What is interesting here is this section. So I can actually configure, I can generate files at configure time. Let's have a look at this CMake file here, which I include. So at configure time, I can execute some commands. For instance, here I execute a command git something, 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 which will figure out the git hash. And it will place the git hash into a variable. And then I can use this variable in CMake and get that thing into the output. Okay, now that I have really just 5 more minutes left, I want to show you 2 more things. And I didn't go into any details. This will come in the afternoon in the tutorial. I want to show you 2 more nice things where CMake really shines, and that is, I will go and enable the testing. And in the testing, something interesting happens. Because in the testing, this project implements some unit tests. And the unit tests in this project, they use Google Test. There are, of course, many other testing libraries. And without going here into any detail, the remarkable thing that I want to show is that in CMake, I can now I can let CMake download, configure, and compile a project which is sitting somewhere here on a GitHub, but it could be on a URL, it could be anywhere. This project actually happens to be also a CMake project. So it will fetch it, configure, and build it, and then it will link it into my unit test. So this is a project that is not in my project. So the target is not here, but we will fetch it from the web, and we will see that. So now, if let's do a new build, I can do this because that's really no problem, because I always, when I remove the build folder, I removed everything that has been generated. I can start afresh. And if I configure now, you will see that it stops a little bit here. And the moment when it is stuck, now it's unstuck. When it was stuck, it actually downloaded Google Test. So Google Test is now somewhere here in my build folder, doesn't matter where. But when I now build my project, you see that it doesn't only build my things, it also builds this external module and links it. And the external module can be somebody else's code. It could also be my own code. So it allows me to modularize my project and distribute components separately, and CMake can nicely tie them together. And now I can run the tests. And here there are two tests that verify whether the thing is adding correctly and subtracting correctly. But the nice thing is, if I do ctest -j2, I can run these two sequential tests, which I defined in CMake. I can run them in parallel if I have now two cores available. And you will see that it started both of them at the same time. So this allows us, very often we have test sets that take more than just a few seconds. It's not infrequent to see test sets that take an hour or two. And this can really help me to make use of all the cores that we have and run them at the same time and not one after the other. Okay, there is really much more to show. I will not show the make install, but it works. Let me give you an outlook of what to expect in the tutorial. So in the tutorial, we will look a little bit more into detail. We will learn how to build, how to link, how to detect the environment, how to detect libraries, and how to link to them. We will learn how to create these tests and also how to download code at configure time. There is also a section where I will discuss some typical pitfalls that people fall into, and I fall into them as well when starting with CMake and when projects grow. Also, Anthony mentioned that tomorrow, so when there is the hands-on in the afternoon, tomorrow afternoon I will be traveling. So I'll be in Oslo airport, but I will be somehow available, and I will be helping through Slack. And I also really look forward to, so don't hesitate to ask many questions. Tomorrow afternoon can be some other day on Slack, and I really want to help you out debugging the projects. So I'm really looking forward to that. And maybe we have some questions. I just need to find the chat and the personal overview here. So I don't know who's chairing it. I can also take the questions. Should I, or?
I can do it for you if you prefer, Radovan.
Yeah, so maybe I will just take them in the order that appear here. So François?
Yeah, I'm not sure. So it's not directly, my question is not directly about CMake, but maybe yeah, I'm not really sure exactly where to ask this question, but you said for CMake you have different backends like GNU Make and Ninja. I've been seeing Ninja more and more often. I was wondering if you know what is the main differences between GNU Make and Ninja, and when could Ninja be more advantageous than Make? But maybe this is not the good time to ask this question.
I think it's a good question. So I have used Ninja some, but actually just to test this material, also test when we wrote these like tutorials and this cookbook with Roberto. In my sort of production work, I use Makefiles. My very naive understanding is that Ninja can produce faster build, which sounds a bit, I think maybe a little bit more efficient build setup.
So in that sense, it's more like a replacement of GNU Make.
Yes. So it's an alternative to Make, Ninja. Yeah.
Yeah, if I can answer this one because I know the answer.
Okay.
So yes, so the philosophy behind Ninja is to say, well, when in GNU Make, for example, GNU Make has become too much powerful in the sense that you can do some shell expansion inside the. There are lots of complex functions that GNU Make can do, and because of this complexity, it has to think a lot before it can start to execute a rule. So the idea behind Ninja is to say, well, doing all this intelligence to do shell expansion and everything could be done by scripts outside that produce a stupid file, and Ninja can just read the stupid file and execute the rules without thinking and go extremely fast. So Ninja is meant to be to make some the fastest possible parallel builds. But then you need to have an external file that is going to an external script that's going to produce all the chain of dependencies of your files. So if I can say something also about Ninja, so I moved to Ninja a few years ago, but I discovered a big problem with it is that the limit of the length of lines, there is a hard limit, and sometimes it fails, and it takes months before you figure out why it fails. It's just because it truncates lines when they are too long. So too long is I think it's 4 kilobytes, but as you generate those files with the script, you can produce super long lines, and in that case, there's a failure. So I think about moving back to Make because of this problem.
Okay.
Thanks a lot for the background. Actually, I'm sorry, I will just show something. It will take 1 minute. It's the most important thing, and I forgot about it because I think we are many Fortran developers here, and I wanted to show you this thing that. So I will add a new Fortran file, which doesn't exist yet. I call it something, and module something and module. So it doesn't do anything useful, but I will just here do integer some number. Okay, and in my project now, I need to use this module. Use something, and I need to adjust so that you can see anything there. And you know that this is really difficult in Fortran because it has to compile something before it compiles the module. But the beautiful thing about CMake is that I just need to list the file, and it doesn't have to come in the right order. It doesn't matter. I will put it at the end. Something, and it will do the right thing. And now it understood that it has to build something before it compiles add. I just wanted to show this because that we have many Fortran developers here. This is a huge lifesaver. Sorry for the detour. So there is a raised hand by Leopold.
Yeah, thanks for the great presentation. I was wondering about this example you showed with tests and fetching essentially the test suite automatically. So in a way, this means you can use CMake as a package manager. right? So kind of using it to pull in dependencies into your project. And I was wondering, is that a good practice in general, or should one rather use then things like Easy Build, Spark, Conda, or I see you're using Nixos, for example, Nix or GUIX or whatever?
I think that's an excellent question. So CMake can be used to really package together. So not only collect, add, configure, or build time the project out of libraries. It can be own libraries, other people's libraries, so it can do that. It could also be used to actually package the software. This is also one of the points where it's easy to go a little bit overboard, because suddenly I can now decide, oh yeah, I will implement all of my different codes separately, and I use CMake to tie together. I think it can be nice for development. One downside of it is I need network. Okay, today we have network almost all of the time, but to fetch something at configure or build time, I need the network. So if I realize that when working on an airplane, I will maybe regret this. For packaging and distributing software, I would still recommend to go for the standard packaging solutions like Spark, EasyBuild, Conda, maybe. There is also Conan, which I never tried out for like C++. There is now the Fortran package manager. So I would go for the standard solution. I think I would not use CMake for that, although it can be used for that. So here I would only use it if for something maybe that is not, here I used it for the testing library, which is, of course, testing is essential in development, but you could imagine shipping your code and not requiring your users to actually test the code. And then it could be okay.
Thanks, yeah.
Yeah. Then there is on my list, sorry if this thing reshuffles, but on my list next is Evgeny.
Yeah, I think Nick was before me, so I can.
Oh, sorry. Yeah, this is just so.
No,
also,
it's okay.
The organizers, let me know if I use too much time. We can also move some of the questions then to. So let me know. But otherwise, okay, let's take Nick.
Okay, thanks for the presentation. I have two small questions. One, how does it handle fixed form Fortran, say Fortran 77? Mm-hmm. And two, you showed a little bit of this help in specific commands, but what generally troubles me with CMake is that different projects uses different naming conventions for variables. And is there a way to see which configure flags or which environment variables you should choose to alter to manage the build in a custom form?
Mm-hmm. Yeah, two great questions about the fixed format. No problem. CMake will understand uppercase F77 or uppercase F or uppercase F90 as to be preprocessed. Oh, sorry, actually I mixed several things here. So okay, now
both are good. Yeah, the preprocess is also important. Yeah. So
yeah, so preprocessing, no problem. Also, fixed format is no problem if it's .f. So we built a couple of projects which have like 20, 30 years of code in it, mixed Fortran 77, Fortran 90, so that is not a problem. Then about the second question, different conventions, and maybe also coming back to, if I understood actually the question correctly, it hints at something that even this may not be enough in projects, or this, because very often we need to actually tell the project what compiler, or what do we want MPI or not. We need to give it a bit more options. And we can give these options through the CMake command line interface, but what many projects do is that they create a script in front, which can maybe look a little bit like configure, which under the hood will call CMake with lots of flags, just to make it more convenient for the user. but it can lead to the fact that projects, although they use CMake, they can actually look really different to the user because they provide a different front end to it. If I understood the question correctly. And then how to standardize it? Well, if I would do something like that, I would try to make it behave similarly to Autotools, because this is what people are often used to. And so if there is an option to set the prefix for installation, it's good to call it prefix and not something else, just because this is what people will expect. Then I see Evgeny and Christian.
Yeah, so if I may. So the question I have is, it's related to so you showed that you can use subdirectories in your CMake file, which brings us to the point, because so we have something similar in Autotools, which is called recursive makefiles. And so the question, I know that, for example, when you have a project which has several directories and each directory has its own makefile for Autotools, it's a bit hard to debug, especially if it's the first time I download the project and I try to understand how it's built. So is there some kind of good practice for CMake, or what's your experience with it?
Yeah, so that's a great question here. There are several ways of doing it. As in, what we did here is that there was one main CMake list, and that's the only place where I defined the project and the language. I do have these CMake lists here in these subfolders, but they are in the same namespace. They are part of the same project. They just help me to define things closer to where they are. So then if I add new tests, I only need to add them here and I don't have to go some other place. So that's one way of doing it. But what you can do in CMake is you can also put separate CMake projects into subfolders. So, and they can even be on a different place. I mean, you can fetch them then. So they can be on a GitHub. So then they are their own CMake projects with their own language and their own definitions. This allows you to really isolate the namespace if you need to, but it can make debugging complicated, especially if you. So here we fetched this library here, Google test. But what if there is a problem in there? This is a code that is not in my repository. I can't really modify it. So if I want to modify it, I need to send them a pull request or I need to fork it. So when things are then more isolated, the advantage is separate namespacing. This can be good for really, really big projects. Normally, I recommend to keep it simple. Start with one, then split it up into several CMake lists, but still keep the same project. And only if you have to, then go for different projects, which are then tied together into one big super project, super build. Hope that answered the question. And
yes, thank you.
Christian?
Yeah, maybe also an answer to Evgeny. So in Autotools, you can also have just one single makefile .am and include all makefile AM snippets from subdirectories. And then you have just a single makefile where you can then use all the parallelism that is available then in Make. This is how we do it, and this, I think, makes stuff clearer and it's easier to debug, and you define stuff where you need it, but you then just include it into the top level makefile. But now the CMake question. So is there a way to create some tarballs, so like we do in Autotools, that you can then ship to your users, or is this not a concept used in CMake?
Oh yes, thanks. Great question. It is definitely a concept. we do that, for instance, in the one of the quantum chemistry codes. And I'm hoping that my screen is still sharing here, but this would be, it's this part here. So CMake can package everything up into a table, or actually any other zip, I don't know, archive. And it can be either a source package or it can be a binary package. So then you get this table, and then everything is in the right places, everything is there that needs to be there. And then one can either install it from sources, or the binary package can be binary table, can also be this RPMs, DEP, some other formats that I'm not familiar with. Yeah, yes. In the tutorial later, I will not do this. We will really explain. We will explain the building. We will explain how to also generate some sources, because that's really nice example with this git hash. And what we will do is then show how to get like compiler information into your output, because that's really nice to have in your output. How is the source code compiled? And we will also do some testing.
Yeah, thanks a lot. And so I really liked your presentation, and so lots of stuff that you showed, for example, also getting the git hash. This can of course be done with Autotools as well, but it's way more complicated than just to write some lines of code you did there. And well, yeah, if I have to start a new project, I think I would use CMake, and just to get more experience with it, because the Autotools way feels sometimes really quite awkward when you know about how programming is done nowadays, using some Python stuff, for example, which makes life so much easier. But to figure around with this weird M4 syntax, which is great if it works, but until then you spend lots of time and you are quite frustrated. So
yeah, I'm looking forward to actually learn Autotools, because that's something I never learned. And okay. To me it feels very magic. It actually, for me, it almost always works, but I would like to know how I can tweak it. So I'm looking forward to the...
Yeah, right. Your own M4 macros.
Yeah, but sorry for going a bit here over time, and thanks so much for listening, everybody. I'm looking forward to the tutorial later.
Thank you, Radovan. So I think now we can stop speaking ourselves and let the participants present their code. How do they have any make files, a build system, or whatever. So I made a little list of codes on my computer. So then, if I can find it again, I will try to ask you to present your code. So then you can decide who is going to do it. So let me find it. I'm a bit lost in my computer. Here it is. So yes, we can start maybe with the champ code. So is anybody from champ willing to present how to install champ on a new machine?
Yes, Anthony.
Ravindra?
Yeah.
Oh, can you put your sound a little bit up, please?
Mm-hmm.
So you can share your screen if you want to.
Yeah.
Oh, very good. Thank you.
Can you hear me now?
Yes, much better.
Okay.
We can see your screen.
Okay, so we have this champ code. It has several directories. The main is the source directory here, and tests, and it currently uses only CMake to compile. So we have this main CMake list, and the SRC has several folders, and each of them will have their own CMake files. So for that, I have created say 2 separate CMake commands to compile them, where I give the Intel compiler, or for GNU I give GNU compiler. So let's see. So it basically goes through this header. It prints out some useful information, which compiler I'm using, which version, what are the MKL libraries and its locations. I also have a macro for finding HDF5. If it finds, it will print it out. We also have dependency on a TREX IO library. So I also find it, and if it is found, it will print this information. We also print some Fortran compiler flags. This one is dependent on the architecture, so it will find automatically. We also print this Git information, but I do it in a very naive way. Maybe I'll use the way Radovan was using. Yeah, and it prints all the compiler flags. Then it compiles all the package. Yeah, that's it. And it has created a bin directory, and I will have all the executables there.
Okay.
Right.
And
Full, yeah. Go ahead.
Do you do some kind of source distribution tarball, or it's something you never do?
No, we don't create any tarball for this package. I can show you the CMake. It would be nice to get an idea for that. How I do the things here. First, we declare some minimum version, and then we need all these 3 languages. And here we just define what are the directories we are going to use. This was some basic information. It was printed in the header. And here we find the find MKL. I think this is a macro which I took from the GitHub repository there of CMake. We also use this find HDF5, which is also from the macro repository. This we wrote for TREX IO library. It's in another directory which we can use like this, include like this. Then we find out some architecture here, which architecture this code is running on, and based on that we use some vectorization, and we declare some flags which will be included in the Fortran as a Fortran flags later. Yep. Here we get all the Git branch and Git hash, which will be printed inside the Fortran source code. That's why we need these two to keep track of the development. Yeah, this one is for GNU compilers, and this one is for Intel. We might add some more vendors also there. And here we list all the subdirectories. Here are some conditional linkings. Yeah, but I needed some help from the developers. Like I do some things very naively here. Like for example, the CMake. I wanted to do some conditional compiling, and so for example, if TREX IO is found, I compile in one way, and if it is not found, I compile it in another way. But this is like just a repetition. Only one file is extra here. So I don't know how to do this because this is just a set variable in CMake. So I had to repeat this whole portion just to include one file at the end. Yeah, but overall, this is very easy to work with. It's much convenient than the Autotools.
Okay, thank you, Ravinda.
Yeah.
So
Stop
then
sharing.
we can go to the GAMCore code. So who from GAMCore wants to?
Oh, okay. Can you hear me?
Yes.
Okay. So I share my screen.
Yes, please.
And sure. Okay, good.
Yeah, we see your screen. It's a bit small. Can you make it a bit larger?
Ah, yeah, sure.
Still small. You have very good eyes, all of you. Adam, I think we lost you. Adam disappeared.
Okay. Yes. So okay, this is if you have GAMCore folder. It is come from our repository. Now we have to go into this folder. We have to create a new directory for object files. Then we go to it's the fun source files. The directory of our it's the fun source files, and run our make file, because it's the fun to build it's the fun. We have make files for default one is for Intel compiler. Then we have make file, separate make file for G4tran, and we have a make file which is common for this building process with i4 and G4tran. And so we use make, and this is we use make default make file for i4. Okay, and now we're building the fun. I don't know, it can take a few minutes. And okay, it's still building. So generally, as I said, we have separate make files for G4 and for Intel compilers.
Okay, so when you distribute your code, basically you give the Git repository to users, and they choose between those two make files, and then they
Yes.
adapt. Okay.
Yes, right.
Okay, and so so from what you saw here, you will probably use CMake rather than Autotools.
I think we prefer CMake.
Okay.
Because generally we use only this default makefile for i4, because we use Intel processors on our clusters. Okay, I get a message that there is a problem with sound. Do you hear me?
No, we can hear you. Yes. Yes.
Okay. Oh, I thought it would be much faster. Oh,
yes,
yeah.
because you have Zoom, we probably
Okay.
will.
It's ready. Okay. So after building it's fun, library, we have to get back to GAMCore folder, and once again in GAMCore folder we have two separate make files. So default one for Fortran for Intel compiler, and this GCC for the Fortran compiler, and this is a common part for both of them. Yeah. So we just run make. That we can use more cores. Bunch of warnings, but nothing to worry about. Everything goes right, and that's it. When it's built, it's generate GAMCore executable. But we need 1 minute, I guess. So it's we have two steps. We have to first we have to build XFN library, not only for the first time, and then we build GAMCore itself. So two-step process. And of course, we have to create the directory for object files. So it's the 0 step, you know.
Yes. Okay, so it's good because now we have a code that can start from scratch.
Yes, exactly. Okay, it's built. We have GAMCore executable in the main directory. So that's it.
Okay, thanks.
Thank you.
So we have also the fdict code. So I don't remember who.
Yes, that's
yes.
me. Can you see the screen here, fdict?
So I think we still see the screen of Adam.
Oh, I have to stop. Sure. Yes.
What about now?
Yes, we see fdict. Yes.
Okay. Yeah, so fdict is a small Fortran dictionary tool I built, and it's currently being built with pure make files. And I tried to do, I created a small project called CMake for containing make field stuff with directories and libraries and stuff like that. So it's basically a self-maintained make file build system. So what you can do is you can go into an object directory, and then you need to specify your top make file, and you just specify where you have your source code make file, and then you can do an out of source build in this way. Then you can also define you can override defaults by using a setup.make file. You can specify prefixes if you want to do an install, and you can override compiler flags if you wish to do this. And then you just type make, and then you execute a bunch of tools. So what is a little bit problematic for this source code is that it runs a few shell scripts to generate the source code. You could do this with fib or whatever, but for now it's a shell script, and that is what complicates this build a little bit, and relying on other commands as well. And this is where I would like to see the different solutions in, say, Autotools or CMake. So, of course, I have something more complicated in mind, but this is a very small utility library that could make use of learning how to use CMake and Autotools.
Okay. And I see you have a mason.build file. So you have been trying with a.
Yeah, so so this is something that was contributed by one of my coworkers, and as far as I know, it works, but I haven't tried it out yet. I have also played a little bit with CMake. I think this is where I want to try out, because Autotools has some other problems that I basically agree with the first speaker about we should try something else. I'm not too fond of CMake either, but I'm here to learn. So
Okay, thank you. So next code will be Quack. So Quack, I think it's Jan or Enzo.
So maybe I'm not the best one.
We don't hear you. Can you put more sound on your microphone?
Is it okay?
Yes, better.
So maybe I'm not the best one to speak about Quark because actually I don't use it, but Enzo is actually using it. So I can share my screen.
So we don't see it yet.
Yeah, it's okay. Okay.
Can you make your font a little bit larger?
Yeah.
So I need to say that I did the scripts that Ian is going to present, and I'm not proud at all about what I have done. So it's a good bad example. So
because actually I just speak about the Makefile, not about the dependencies.
Yes.
Okay.
Well, you should probably explain when you come to a new machine what you have to do.
Yeah. Okay. Because so we have first Makefile in the first directory, but I think it's not very important. And when we go to the source directory, we have another thing which is a Python program to produce another Makefile. So Anthony made something like that in order to produce a Makefile, and in the different directory we will find again another Makefile. So it's a combination of a lot of Makefile, and it's not very good. So it's for that reason Anthony is not very proud of that. And we have another problem because we have some dependencies. So to install the dependencies, for example, the NumGrid, we have a script to install the dependencies with a git clone, and it's not very efficient because in some cases we have some problems, and we are looking for a better way to do that.
So if I just can add a few things on that code. So we have been using Ninja for this one. But the problem with Ninja is that users are not used to it. So users are used to type make. So we have make files that are just calling Ninja so that the users don't really see what's happening behind. That's a stupid workaround that makes things more complicated than easy in the end. And so the code is in the SRC directory there are multiple directories with Fortran files inside, and so the make Ninja script, what it's doing, it's just exploring all the files and creating these dependencies between the source files. And so for each directory there's a library .a static library which is built. And at the end, everything is linked together. So the bad thing with this code is that to get the dependencies. So we try to make things simple in the sense that there is a Makefile that's going to check to do also the wget and the git clone, and then trying to build the package, because we put inside Makefiles that the rules to build the library is to fetch the package and to build it. But then later on, we realized that it was bad practice to do things like this, because it was really, it doesn't give enough freedom to the user to install things in the way it should be done. So this is, it works fine on our systems, but it's really a bad example of portability. So I told Jan, well, it could be a good opportunity to break everything and do things in a proper way during this hackathon.
Yeah,
So if you
and
want to back the example, then you can have a look at this.
in addition, I think we have a problem with the last version of NumGrid. So using this kind of method that doesn't work with the actual code. We have to take a previous version of the NumGrid program.
Yes. And so also, I think it's a good moment to explain why it's bad to download the software and try to install it for users. So here, the situation is that when the users take the code and run all these automatic scripts, they are not able to install NumGrid because NumGrid changed the way it's installed. It's not the same sequence of commands. But the thing is that the users, they ask us to Quack developers, I'm not, it doesn't work because I'm not able to install NumGrid. And so they are directed to the wrong person to ask the questions. And so it's not a sustainable way to do things. It's not good. It would be better to tell the users, install NumGrid by yourself. And then once you're ready, come back to Quack so that they will read the how-to of NumGrid and they will do the proper commands because it's updated. They will not use an old way to install a new NumGrid. So it's much better this way. And also, if they have a problem installing NumGrid, they will contact the NumGrid developer, who I will not tell who this person is. So they will ask for help to NumGrid instead of telling us that it's not working. So that's a good example of what you shouldn't do. Try to install packages for users and let the package software package managers do it. And that's also why we have a presentation at the end of all these software packaging tools. Okay, so we are saying a lot of bad things today about about our stuff. So we can now try to move on to Turbo RDB.
There's a question by Radovan. Maybe do you want to ask it?
Oh yes, Radovan.
Yeah, so I just want to give a quick comment there that, yeah, sorry for this NumGrid code. I see actually a couple of places. Yeah, so don't judge me. Things are changing, but really great point that you made. I fully agree. If you depend on code that is outside of your control, I think it's actually better to use standard packaging solutions like Conda, EasyBuild, and then require this from them. So if you want to depend on a code like NumGrid, tell the NumGrid developers that I will use it if you ship through standard solutions, and then everything else is out of your sort of somebody else's problem because it's otherwise not maintainable. So I fully agree with that. I made the same experience, and sorry for the troubles.
No, it's so we learn from mistakes. We have done lots of mistakes, so we have a lot to teach. So somebody from Turbo wants to.
Yes, can you hear me?
Yes.
Okay, so I'm gonna share my screen. I want to share. This is wait, here's desktop. Okay. So can you see my screen?
We can see your screen, yes. But you have something in the middle. You have your Zoom window in the middle.
Do I? Maybe.
Yes, it's better now. Yes.
Okay, thank you. So our code is Turbo RDB, and it's maybe not the newest code. It was started and developed in 2003, but for a long time it was only an in-house code. It's basically a quantum Monte Carlo code, and it uses a lot of quite difficult algebra and algorithmic differentiation. It has a lot of Fortran 90 code, and currently it uses only basic make files to build it. So I can show you how it looks like. This is basically, I don't know, enlarge. So I think this font should be large enough. And basically, if you are familiar with VASP 4 and 5, how it was built, you basically have to define only make inch. There is a couple of make inches defined here in config directory. basically, whenever some of us users, developers uses on some different machine, it just defines the new make int make include, and for my machine, basically it looks like make. Unfortunately, I'm sorry. Can you see my screen? I was logged on the
yes, you can see very well.
My remote yes, I was logged on my remote machine and something happened with the connection. So this is on my local desktop. Basically, yes. So there is this we make that include in the INC, and basically there in the example make includes there are maybe basically the path to the there is a variable for the make path to the library tools. There is a definition of the compilers and all the flags, and then you just only have to make. I haven't loaded the compiler, so this machine to make serial MPL all, and it's gonna make all the executables. There is only one big caveat. Basically, in the source directory there is this make txt, and I think this is going to be the biggest challenge for us, because we might plan to write CMake build system, but the problem with Turbo is for reasons unknown to us, there are a few object files. If you try to compile them with the most most aggressive optimizations, they will not produce correct object. There is going to be the code going to be corrupt, and this is a thing that we just discovered by testing them that didn't work, and we defined a special list of objects that have to be and can be compiled aggressively. And the problem is, on some machines we have to interchange, we have to exclude some of these files from this list because they cannot be compiled. And if we haven't compile them aggressively, we will have a huge performance loss. So from this important routines that do most of the maths, one has to check which one he can or cannot compile aggressively. So good question is, I don't know what causes these problems. Basically, we just test if -03 is possible or not from that particular object file. And as you may know, -03 is basically a flag wrapper for a lot of different tricks for the compiler that he can do, but we haven't found what causes these problems. And one workaround I have in mind is to build a set of test tools that during the compile time they're going to compile these object files, test them, and the ones that doesn't produce correct results will be recompiled with a lower optimization flag. Yes, this is so. So I think from this point, the compilation quite easy. One has to, well, only one thing is there is this make that txt standard, and before one wants to compile this software package, one has to copy the make that txt standard to make that txt, and this one make txt should work on most of the machines, but there are some exceptions, and you can find those exceptions in the config in the config. As you can see, I know, yes, this is a special, this is special make TXT for Marconi 100 machine. So some time ago, Kosuke Nakano made also a CMake builder, but he advised me not to use that because at that time I was not very experienced with the CMake, and it may produce some corrupt builds. So it exists here, but as far as I know, no one's used it as using it, and yeah. So this is basically how TrueBug is built. So our goals for this hackathon is basically build some suitable build environment. Then as I told you, now it's basically done by hand. One has to copy the closest make in that is to his system, and then just adjust it for its particular purposes. And yes, and there is this problem with this. One have to specify the list of routines, object files that cannot be compiled too aggressively, and well, and I hope in the end we will have a nice code, nice build utility to compile Turbo. So if you have any questions about this, I'm happy to answer them. But I think it was quite straightforward.
Thank you, Otto. So I see now it's already 12 o'clock, because we took more time for the presentation of CMake and Autotools, and so I think it was good to spend time presenting these tools. So I would like to thank again the two presenters. And for the presentation of the codes, what I propose is that we continue this in the first hands-on sessions that will be tomorrow afternoon. Before we all start putting our hands in our codes, it will be nice if we can continue to present the codes. So before going to lunch, I just have a tiny question for Radovan that can maybe help you decide if you will go for CTools or Automake. So Radovan, when you use CMake, suppose your Fortran files are not generated by the developer, but if the Fortran files are written by scripts, will everything work easily, or does it need a lot of effort to use CMake?
I don't expect any problems there. So no problems. They can be generated. They don't have to be sort of the Fortran files. They don't have to be pretty. They don't have to have a certain form. Because all. Oh, okay. So maybe let's take a step back. What does CMake do with them? Of course, it passes them onto the compiler, and the compiler does its thing. But it does one more thing, and that is it goes in and figures out the dependencies.
Yes.
So it's a Fortran 90, right?
Yes.
And the dependencies, so it will look for the use module only this and this and this and this. And it has a good like regex scanner. It could be that if this is very, very strangely formatted, that it cannot see that, but I haven't met this problem.
Yes. So my question was, when you run the CMake command, the Fortran files are not yet there.
Ah, okay, I see.
What's going to happen? Because there is also this dependency scanning, and so CMake doesn't see the files yet.
Yeah, I see. Now I understand your question. Sorry. Yeah. So that is possible because you can then tell that some source files are generated.
Okay.
But I don't think I've ever tried to generate Fortran files.
Okay, so it's not blocking this aspect.
No, I think it will work, but I have never tried it. I have generated C++ files. Where also the dependency works, because also there it goes in and figures out header files. So I expect it to work also for Fortran files. Okay. And then we will tell CMake that certain files we will list them, but we will tell that certain files are not there yet. They will be generated by this and this target. So do this target first.
Okay. Yeah. So it's like same kind of thing as usual.
Maybe it's better to run the generator of Fortran files before running CMake.
Yes.
So that's an alternative, but it of course it would be nice if you can kind of as a developer you can edit the generation scripts and then you hit make and it will hopefully just redo what needs to be redone. So I'm quite confident it can be done.
Okay, so thank you all for this morning, and so let me see when we need to come back. I think it's 1:30. Let me check again the schedule. So it's somewhere in the general section. Yes, yes, 1:30. Okay, so let's meet again at the same Zoom link at 1:30. And bon appétit, as we say in French.
Bon appétit.
Appétit.
We'll come back from the lunch break and I will take the screen and explain a bit what the plan is for this afternoon. Just resize here. Just a practical question. Are there people participating now in the tutorial who were not there in the morning? Just that I should explain sort of the setup here, or maybe it doesn't hurt. So I'll be using this kind of portrait, more vertical sharing so that I can have both, so that I can share both my terminal and the material, but also that you can do something in the second half of your screen. I mean, maybe you have more screens, but I have only one, so that you can. This will really be a hands-on tutorial workshop. And coming back to this page from this morning. So in the morning, I made this very quick tour over motivation overview and brief tour with some example project. Now, the plan for this afternoon is down here, just to show you a bit what to expect. So we have 3 hours planned. And of course, 3 hours is a lot, so we will take breaks. I will really make sure that we take breaks every hour. And hopefully this is really sort of informal, in my opinion. Ask many questions. The more questions, the better. So the less monologue, the better it will be. We will, in this tutorial, I will do some short explanations. I will demonstrate things in the terminal. I invite you to type along. There will also be exercises. And we will start really simple, but then we will build it up in a nice progression. So we will start with a very simple one source file project. Then we will add more source files. We will talk about how to compile, how the targets work. This is really the central thing in CMake. How to build larger projects, detecting the operating system, detecting libraries, linking to them, testing, and also this fetch content. And at the end, we will have a discussion about typical pitfalls. Many examples, most examples will offer both, there will be C/C++ and Fortran. So you can take the one that you like better, where you feel more at home. All right, here about what to. So my goal is not that we become CMake experts in 3 hours. Also, the goal is not that we remember all the syntax. This is, I think, not important. What I will try to achieve is that we get it, that we understand the idea behind it and how to start. So I give you a good starting point. Also, that we recognize patterns which are less maintainable. certain things didn't fit into a 3-hour tutorial, so I will not show. Still happy to talk about it, on Slack or somewhere, is how to probe compilation. So you can, like in Autotools, you can actually try to compile something, and then depending on the result, then CMake can do this or the other. We will not discuss composing CMake projects out of non-CMake projects. So that's possible. You can actually put together different projects that are not CMake, and then CMake can do the whole thing. I will not show that. I will show how to compose CMake projects. We will not talk about super builds, cross-compilation, GPUs. I mean, these are workshops on their own. I think I'm already really happy if we are able on a CPU to really build and understand. Also, we will not talk about how to mix compiled languages with like Python. It's possible. There is also PKG config, which I will not mention, but it's again possible. This is a plan B in CMake. So if a find library module doesn't exist and you don't want to write your own, there is always a plan B. You can go for PKG config, but I will not talk about these things. Okay, and we will start really simple. For some of you who write CMake, certain things will be completely familiar. I still think that we will all learn something new. Also, I will learn something new. I mean, I will also make mistakes, and there will be things that I don't know. So I think all of us will benefit, but again, please really unmute talk, because I will try to watch here the chat. But for me, it's just easier if there are many questions. And yes, and this is, I encourage to go here to GitHub and either clone. So if you are familiar with Git, you can git clone the repository. If you are not familiar with Git and GitHub, you can also download the whole material. And in here, there is actually the whole tutorial. I mean, all these episodes are in there, but I want you to have these examples on your hard drive. And later when we go through them, some of them there is like a problem and solution. So for instance, multiple folders. So there is a problem folder and a solution folder. And then in these folders, you often find also C++ and Fortran. So you can take the one that you like better. Okay, any questions up to this point? If not, then I will jump into the first episode. You can reach it either through the schedule here. You can also, on the left, we will be following here. So first hour, these 2 or 3, second hour, third hour. And maybe we don't manage everything, no problem. So there won't be any rushing. And the first one is we build a hello world together. This is also a moment if you are unsure about your installation, like CMake installation, this is something I'm happy to now help. Also, if you can try, like if you have CMake available, what you need for this tutorial is CMake and either a compiler that can compile Fortran or a compiler that can compile C++. The version itself, I think it should be relatively recent. I think the examples require 3.14, but I think they also work with 3.0. So please let us know if you have some like installation troubles. So the goal of this, the first exercise here, and the first one we can do as a type along. So I recommend to open a terminal and type with me. And we will build a hello world source. So take the one that you like better, either Fortran or C++. I will maybe take this one here. And I create a new folder. I will go out of this workshop. And I create a new folder. And you can either watch me or type along. And in here, I will put this hello CPP or hello F90. And then we also want to create this CMake list.txt, which tells CMake what to do. And here's a very short one. So again, please try either the C++ or the Fortran one. And in CMake is case insensitive, so it doesn't really matter which case you use inside the CMake code, but the name of this file has to be this way. So it cannot be like a small CMake small lists. It has to be CMake uppercase lists. And in there goes the, no, not this one, but this one. So you have now two files. One is the source file, one is the CMake file. I'll just open here on Zoom the participants so that I can see. Oh, I clicked something wrong, I think. Okay, I hope I'm sharing. I clicked the wrong button. I just want to see participants in case somebody raises hand, but also please, in my opinion, you can unmute and ask. All right. So we have these two files, and then we can configure. So the configure step will generate a make file. Later, I will also show what to do if you don't want a make file, but you want a Ninja file or something else. And this tells CMake, this dot here means here, and I pointed to where is the CMake list. And here I tell where do I want the build artifacts to be placed into. And it did some discovering, and then it wrote the build files into this folder. So there's now a new folder called build. And now you can build like executable. One way of doing it is this. This is the more general way because it's not bound to make files. If you know that you have make files, and in my case, I know that I have make files, I can also go into the build folder and type make. And maybe I should also try it out, hello world. So it seems to work. So at this point, I want to remind it's really good to separate the source folder and the build folder, because now you can have one source folder and you can have different build folders, one for debug, one for optimized, one for MPI, one for sequential, without copying the whole folder. Here, earlier today, I showed that there are these many different generators. Makefile, Unix Makefile is only one of them. And if I wanted to configure for Ninja, this is how I would do it. And you can even pass additional options to CMake. And later we will see that there are many of them are available. So this is one way of specifying the compiler. I set this why we prefer out of source builds. In this example, there were and I see the question. I will come back to it. Thanks for that. Just want to say before we go into the installation is that so far we've seen these three commands. And in this material, you can actually click on these. So if this is a CMake command, you can click on it, and it brings you to the help. So then you see the whole, what are the different options and a lot of explanation. So although here project, what can we do with the project? We can specify like the name, version, homepage, languages. So that's convenient. And a good question that came in on Slack. So did you install with Conda and activate the environment? So that's a good question. So in my case, I didn't, because I have a bit of this little bit unusual system here. But good reminder that we created this environment.yaml, which describes and contains all the dependencies that we should need. So I really hope that this works. And please let me know it doesn't. And also, if you have problems activating the Conda environment, maybe I should have really shown that. Then please let us know. Maybe somebody who is using CMake with a Conda environment could screen share and we could have a look at that. So I should really eat my own medicine and also use this Conda environment. Maybe let me ask differently. Anybody who had trouble running this Hello World example?
Yeah, I was stupid to not. I mean, I'm using Conda environment. Sorry, this is Vijay. I have a base environment running. For some reason, CMake, the pip, the Python module was not installed. So I had to just. So when I ran CMake, it said a module not found. So I had to do pip install CMake before I could get it running.
Interesting. And now does it work now?
Yes.
Okay. Yeah, but yeah, I should really do what I preach here. But I just wanted to show you where this is described. So we, based on this environment.yaml, you can create isolated environment and then activate it. And the nice thing is that at the end of the workshop, you can again delete it and it doesn't really modify the rest of your environment. And one reason why I didn't show it myself is that this is a little bit of a strange Linux system where Conda is a bit difficult. But this is an unusual system, that's why, well.
Yes, but Viraj didn't use Conda. He used directly apt install, so it's very weird that he has to do pip install in addition to apt install.
That is true. So apt get install should be enough.
Yeah, sorry, can I comment? So I think if Vijay has still base environment, so he probably didn't activate the one created with the YAML file. So I guess if the conda env create command executed successfully, and then if you activate the environment, then it should be fine. You shouldn't be in the base environment anymore.
Yes, exactly. Yes, Evgeny is right. Yes.
Yeah. So that's really good point. So when I work in Conda, and I do work in Conda, but just not today, is I never modify the base environment. It's good to consider the base environment as a read-only thing. And for anything that we need to install, I create isolated environments because then they are well documented and also disposable, and I can have several of them. So that was really good reminder here. Thanks for the notes. So back to here. We are with the executable. Everything worked well. Yeah, 3 commands. And again, reminder, you can like kind of right click and it brings you to the CMake help. And the add executable, we give it a name. And here I list one source file, but I could list several of them. So if you have a project which has 10 source files and they all compile into the executable, you can list them here. And also you can list them on like line by line. So it's and in the Fortran case, you can list them in any order, doesn't matter. So it will figure out it will compile them in the right order. Good. So now we can take it one step further. And now we want to have a little bit more modular Hello World, because only very rarely we have one source file. We like to split projects into several files. It makes because then we don't have to recompile the whole project every time we make a change. And also it makes it easier for people programming because they don't need to just maintenance and a better project organization. So here, this will be actually an exercise for you. I will also do the exercise, but I will do it like silent so that I don't talk all the time. Where now we have a main code. Oh, actually, let me just, for fairness, let me now look at the Fortran one. So we have a main code, but the main code uses a module greeting. And there is this say hello function. So this is the Fortran module, which provides a say hello function, and it returns hello world. And I'm sure that there are better ways to program this in Fortran or in C++, but here the point is to do that now and to solve it in CMake. In the C world, we have now 3 files because we have the main code, we have the implementation, and we have the header file. And your first goal, so you will do it in 2 steps. Your first step is split the code up into 2 or 3 files. And you will see that all you need to do in your CMake lists, all you will need to do is to add them here. And it will hopefully just work. The second step of the exercise, your second goal will be to not compile everything into the executable, but to compile the greeting part into a separate library. So here I define a library. I want to have a library called greeting. I want the library to be shared, dynamic. Then you list all the files that belong to the library. And then we link the executable against this library. And what this private means, we will come back to that. Same on the Fortran side. On the Fortran, the library consists of 1 file.
Radovan, I have a question. So do we have to list all the files by hand? Is there a way to?
Yeah. It's a very good question. I recommend to list them all by hand. We don't have to. So there is a way of globbing files. So you can let CMake discover files. You can just say, please find all the files that end with F90. But I will, at the end of the workshop, discuss why that is not a good idea. It looks like a good idea, but it's really good to list them one by one. And this sounds like a lot of work, but even if we have hundreds of files, we still don't. It's still manageable. It's actually really good for CMake to list them all, because then CMake knows about them and it can track their changes. So recompilation is easier for CMake if it knows which files are there. So I recommend to all list them.
So a follow-up question then is if we are generating files using a script, then we also have to generate this add executable, right? Because there'll be new files which will be generated, for example, depending on the CMake flags.
Yes.
So in that case, like, how should we proceed?
Yeah, so even if you generate files, so this could be a generated file that doesn't exist. It would be still good to list it here. But then I can dig out, there is then a way to say that this is a generated file, so don't expect it to be there, but it will appear at some point.
Okay.
It is, if you generate lots of files and you are really tired of listing them, there could be a use case for actually globbing the files when we generate them. And that's okay for the first compilation, but it can make recompilation more difficult. So also there, I would recommend to actually list them.
So I have a follow-up question on the listing. So can one list them in arbitrary order? And then CMake will find out the...
Yes. So arbitrary order. later we will discuss what we can do with this private and public and interface. So we will later group files into private and public and interface, but it doesn't matter in which order they are here. It doesn't matter for Fortran, it doesn't matter for C++.
I have a question. Don't you consider it's good practice to not specify shared library here in the add library option and let the user decide this at configuration time?
Yeah, it probably would have been better. So you can actually leave this out. So this here I wanted to show how you can do it. Sorry, telephone calling. I will just call back. So you could leave it out, and you could let the command line decide whether static or shared. Would have been probably better, more flexible. Yes. So I want to give you some time, 10-15 minutes, no rush. So this is also time to catch up with the first part. So your goal is split it up into files. And then the second goal is define a library. Which solution did you like better? Discuss pros and cons. We can discuss it together. I think we are all staying actually in this room. So don't hesitate to also ask. What kind of library did you get? Well, we expect that we got the shared one. Try to get the other one. And then you can already also prepare for this discussion, which I would like to have with you before moving to the next part. So we can try that.
May I have one last question before? I would like to, I always use CMake with like just to generate makefile and then makefile. But if I would like to use CMake this build, but I want to make clean, or basically to clean the you know what I'm trying to say.
Yes.
How to do that, because I was unsuccessful with this.
Yeah. You caught me there because let's see. Let me see whether I find out how to do it properly. I can show you how I do it, but I just wanted to show you first the proper way. Keep grep clean. I have it somewhere in the material. That's the proper way here. So let's go back to the example, and then I'll show you how I do it, because I'm just really old school. And so this is the proper way of make clean. And why proper? Because it doesn't assume make. So this now, if I now rebuild, it will rebuild from the scratch. The way I do it is I go in and I type make clean, but this is of course bound to the make files. So it generates a clean target for the make file, but this is the more, and it comes later somewhere in the material, because so this is the proper way, like portable across Ninja and
yes, okay. And basically, if I have multiple targets, I basically can specify more targets and compile whatever I want to build, right?
Exactly. You can say my target. You can build target a component, not the whole thing. Yeah, like in make. Oh, wait a moment, I'm in the wrong place. Yeah, and of course now he doesn't know what to do, but.
Thank you.
And I will also do the exercise in the
Excuse me, can I have one more question? No, I can't hear you. Can you hear me?
We can hear you, but I think Radovan is
okay.
is away.
Okay, I see. Okay, so maybe later.
He's back.
There was a question. I'm back. Sorry, I was gone for a minute.
Sorry. May I have just a quick question?
Sure.
About the header files, because I noticed by accident actually the header it compiles even if I didn't specify the header files. So does the CMake find them automatically, because I see it copies to the build directory? So I don't know. Is it necessary to specify these header files?
Yes, that's a great question. So it will work even if you forget to put it in, because it still scans the dependencies. So even if you, where are we? Here we are. Even if you leave this one out, it will still compile. It will all work. What I'm actually a little bit unsure, because it's been a while, what we could try is that try to then touch the header file and see whether it should still work. I think it will work. I'm just thinking, when will this fail?
That's a great idea. I'm really curious.
It's useful if it's useful so that at configure time it will tell you that a file is missing instead of seeing it at build time.
But now try to touch it, and it noticed it had been touched.
Okay.
So even if I commented out the HPP file.
Yeah.
Interesting.
So I think here actually it doesn't matter now. I think it will start mattering once we talk about targets. We will get there, and when we link targets to other targets, and we can propagate visibility to other targets.
I see. Okay.
And then it's more explicit. So in some projects I don't list them because I forgot, and I actually for some time I didn't even know that I had to list them. These days I list them because it makes it more explicit, and then later we will see how we can control visibility of these properties to other targets.
Thank you.
Radovan, I have a question about Fortran. I just run your Fortran example, and when I make a grep mod in the other files of the build directory, I see that so I'm using Ninja to test. So I see that the Ninja files contain the .mod files of Fortran, and so yes, exactly. And so so I changed the name of my module. Instead of calling it greeting, I called it bad name. And so what's happening now is that the gfortran produces a file named badname.mod. And so there is no relation between the name of the Fortran file and the name of the module file without inspecting the content of the Fortran file. You see what I'm trying to say?
Yes.
So this works with gfortran because I guess that CMake knows how gfortran produces mod files, but is this kind of behavior going to work with any Fortran compiler, or do we need to follow the rule that the name of the file should be the name of the module?
Yeah. Okay. So I think that it will work in any standard compiler, but I really only these days I really only use GNU and Intel, so I don't really know what happened to the other ones.
Okay.
So I think it will work. I think the module name and the file name doesn't have to be the same.
Yes.
I still find it very practical to make it the same, not for the compiler, but for the human, because what I find really irritating is that if there is a compilation error and it tells me that there is a problem in module greeting, and now I look for the file and I don't see any of that file, and because the file names are called differently. So for I think for humans debugging, I find it very nice if the module name is the same as the file name, but the compiler doesn't mind.
Yes, but you could imagine to call your file greetings_module.f90 to say that it's and in that, but the module would be called greetings. So you could have a name that's different just for. Suppose you want to put your functions outside of the modules.
Mm-hmm.
You have one function with the module containing the data and one. And in that case, you will have a name conflict you need to solve by TREX. And because I had this typical problem by putting dependencies on mod files, and then I think it was on an IBM machine. I was using a different compiler, and the rule to produce the name of the modules was not the same as the compiler, and it doesn't seem to be standardized to this.
Yeah, on IBM I remember some troubles there, but it's been a while now. I agree that in this case it can be fine to append something there if it's still if I can somehow relate the name to the file name.
Yes.
But not a problem on Intel or GNU.
Okay.
There is a raised hand by Mohammed, but I'm not sure whether this was already asked or is this from earlier?
Mohammed, you have a question?
Maybe from earlier, or audio doesn't work. Maybe we can try later.
Yes. Thank you.
So, okay. So maybe if you need to find a mechanism, so that let me know if you would like more time. Hopefully this worked. Let me show you a few things which are kind of nice, but which might be. So I have changed the CMake file, and notice that I didn't reconfigure. You don't have to. So I only rebuilt. But then CMake noticed that I actually changed the CMake list file, so it noticed that it should actually reconfigure on its own. So I didn't have to go outside, reconfigure, and do all these steps. So it will do the right thing, which means that in practice, I often configure only once, and then I edit, make, edit, make, edit, make, edit, make. We should maybe discuss here. So we made this a little bit more granular. What is a good way? Should we collect all the executables into one source? Should we have one library? Should we have many libraries? Any pros and cons? How do you do it in your projects? Anybody wants to share their view? Of course, it depends on the project. It depends on the taste. So I heard some static there. Maybe, oh yeah, Mohammed is now unmuted.
Yes. Sorry, I couldn't unmute myself. I have a question. I wonder how we can link a directory of the library to the CMake.
Directory of the library.
So the header file and the library, both are in the directory, and I want to link this directory to the code.
Yes, so maybe if let me check whether I understood the question. Also, your microphone is on like super high gain, but it was understandable. So just to check that I understand the question, so I showed you we can do this and we can do make clean, but how can we build with if I want to actually see the compiler flags and I want to see the whole link line, everything, you can do this. So you set verbose to 1, and then I see everything. And just so I will now build with all the gory details. So you can, for instance, see what flags did it use, and just that I understand the question. So is your question about? Okay, then the other thing. So is your question about minus big L? So
no, my question is if I have some folder, some directories, and I want to link it to the this file. How can I link these directories to the file? Here, yes.
So we link actually targets to other targets. And so here, the sources of this target, they are now in this folder, but they could be in a different folder. So what you would do is in your other folder, you would define a library, you would collect the sources to it, and then you link against the target. So in CMake, we want to avoid specifying any paths or source files. It's possible, but we want to avoid it because that makes it less portable. Because paths are different on Windows, library names are different on Mac OS, Linux, Windows, static. So we want to really avoid all that. So
okay.
We will come back to that. In fact, later when we structure bigger projects, we will have libraries in subfolders. So we'll get to there.
Okay, thank you.
Mm-hmm.
I can comment on your question if since you invite us. Suppose you have several executables that share a large collection of files.
Mm-hmm.
If you just list the files after each executable, it will, the way CMake works is that it will recompile the same files for the different executables.
Yes.
So that's a con.
Mm-hmm.
And if you, on the other hand, if you create a library and use this library for your executables, so the advantage is that it will not recompile everything, but the con is that it will relink all the executables, even if they don't use the files that you modified for your library. Imagine you modify just one file that is not in a given executable. It will still relink the executable.
Mm-hmm. Great point. I want to add one more thing to it. So it can have an effect on recompilation and relinking. In the Fortran world, if I put sources into different libraries, it will not scan the Fortran dependencies across libraries because that's not what. So the F90 like use module, it's scanned within the library, which means that I can make it easier for the dependency scanner, but the dependency scanner of course does it in 1 second, so it doesn't matter. But it can, organizing the project into several libraries can actually prevent me from introducing accidentally a Fortran 90 dependency into the project. So it can be helpful or not helpful, but it's good to know about it, that the F90 scanner looks within a library, not across libraries. Because a Fortran 90 module is not really meant to be a library interface, but it's a whole different story. So just summarizing some key points from this first episode here. We have generated a makefile. What we do is we write one CMake list, later we will write several of them, and we define languages that we want supported, Fortran, C, CXX. Oh, yeah, one thing actually I didn't mention is that by default, the build folder, so the objects and libraries, they will be mirroring the source folder structure. You can change that, but that's what happens by default. And now I will go to the next episode. So we will take a break like in 10, at the latest 15 minutes. I wanted to tell you a little bit about compile flags and debugging, because so far it was all a bit black box. It picked some compiler and then it compiled somehow. It's good to know that you can, if you want to pass a definition to CMake, you can do it like this. And then you can pick it up in CMake. I have shown this verbose build. This is the portable way of doing it. This is if something doesn't work and you want to see, or you want to see like, did it pick up this optimization flag or not? Well, because I'm in the wrong place. Or you can do it like I did. You go in, make verbose 1, or you set it as an environment variable. On Ninja, this hopefully works. So you can try this out, clean, and let's build with verbose. Then we see all the details. It would be nice if we can actually influence it, and I will show you how. Also really useful is this stuff, message. So this is like print. It's really good for debugging. Let me put the print somewhere in my CMake lists. You can print a status message. You can also use this if you want CMake to stop there. Please stop here and print this. What happens? You get this message here. And I use that to debug, to print some variable if I'm unsure what is the value of something. Two variables which are often really interesting are these ones. So I will add them to my CMake list, just to print them out. And you will need them later in an exercise, but I want to know what is the compiler and what is the compiler version. And this is one way of printing something to the output. So here it will replace this by the value of the variable. It's a bit like in Bash. Whoa, that didn't work. Oof. Oh, yeah, maybe somebody has an idea why that didn't work. Just a quiz. So I expected this to work, but it doesn't.
Can you show again the CMake list, please?
Yes. So the syntax was actually correct, but yeah.
You are building the Fortran project, so
Yeah, exactly. So in my case, I didn't define, these are undefined. One just a lazy way of defining them is that I can say that this is actually also CFS projects, which is not really true. Another way to solve it is that I go in and change the CXX to compile to Fortran. Maybe a good demo. So now I want to know about my Fortran compiler. And now it should print something. So in my case, it picked up GNU, this version. And this can be a little bit clunky. There is actually a helper. There is a module that is in the sort of CMake standard library, and you can include it like this. And then you can print variables in a nice way. Also good for debugging. I think this will be very useful tomorrow. But also here, I want to do the Fortran. And then let's get rid of this. And what will you just list the variables that you want printed, and then it will do this for you. So that's nice for debugging.
Can I have a question?
Yes, please.
I'm missing a vocabulary for this question, but basically, I noticed it doesn't matter the order of where is the add library and the executable in a CMake list. And my question is, I had this opinion about this. My question is, how I know at which time this print commands will be executed, because there is like I noticed there is no time. I don't know how to explain my question.
Yeah, I think it's a good question. I think it's a very good question. So it will, CMake actually reads this from top to bottom, and this will be printed once it actually reaches this line. But some of the lines here, they are not imperative, they are declarative. So I declare that this is part of the library, and I declare here that they are related. So it will actually continue reading without doing anything, and only at the end it knows that, well, okay, let me rephrase actually. It processes this file from top to bottom. Based on this information, it creates a makefile that has this relation, and as soon as it reaches this line, it will print it. But still, very good question about the order of execution, because we should actually try to write CMake files where the order ideally doesn't matter much, so that if we reorder things, things shouldn't break. There will be some order to things, but later when we split the CMake file into several CMake files, and then we can include them into the main one, we want to really be careful about the order, to not introduce any implicit ordering there. I hope that was some
yes,
somehow okay answer.
And yes, and it is possible in, for example, if I'm not very familiar in how to make, but if I have a how to say some kind of decision tree, like I want to test something, and I would like to define something like a routine or function that checks something, I can put it this inside this function, and it's going to be executed at the time it's going to be invoked, right?
Yes, yes.
Okay,
Yeah.
Thank you.
Yeah, and later I will also show how we can have like an if then else, how we can do options. So we can also in the CMake we can have branching. Right now everything is linear top to bottom, but in bigger projects we need some decision trees. Depending on what the user wants, depending on what is on the system, we may need to decide.
Okay, thank you.
And now, just 5 minutes before the break, yeah, so we can now print. You could have a look what compiler it picked up in your case. You can even try to print something that has been undefined. The CMake code will not stop, it will actually print empty value. But I wanted to show you how you can control the compiler. And there are several ways of doing it. So one way is setting environment variables, a little bit similar like in Autotools, fccccxx. You can define them, and then the CMake will pick them up. Here is another way. So you can define, these are CMake variables, CMake Fortran compiler, C compiler, CSX compiler, and you can set them to something. And if there are many variables, if you want to know what is out there, what does exist, there is a lot. So these are the variables that CMake knows about. And you can query them, you can print them, have a look what is inside, you can modify them. So this is one way of selecting the compiler. Or you can define your own variables. Variables have scope. I will talk about that a little bit later. My recommendation is to minimize the number of variables. So if you see a CMake code with lots of variables, it can make it a bit brittle because this introduces suddenly order. When was it defined? But sometimes we need them. Here are a few variables that we will need a lot. This one points to the project binary here. Actually, I can click on it. It will point to the place where we are building into. So this is the build folder, if you need it. Project source here is the place of the top level CMake lists. And then if you want to know in which folder is the current CMake list.txt, it's this variable here. And you can even get help about a specific variable, like here. Actually, it's the same help as here on the web. And there is one more thing that I didn't say, and that is how can we control if I want debug build, optimize build. This is the way of controlling it. So you set this CMake build type to debug or release or optimized with debug information. And what many projects do is that they set this inside to some default. So some projects want by default to be compiled with optimization. And then you can put this into your main CMake lists. And then what you also want to do sooner or later is to control compiler flags. And you can really, so here is one way of doing it. So if for an Intel Fortran compiler, you can decide that I want this to be always there. I want this to be there when I do debug build. These should be there when I do release build. And for GNU, something else. And for AIX something different. However, this will set it for the entire project. And later I will also show how you can set these only for certain targets. And this can be really useful if we remember the presentation from before lunch about this one project where you needed to lower the optimization on a couple of files. This can be one way of doing it. So you can define a target which should be with less aggressive optimization, and then you can set flags on the target. So it doesn't have to be for the entire project. And I think there is a question, Otto, if this is not an...
Sorry, so it was from last.
Oh, so from before. Okay, good. All right, so I will just get the overview here. Where are we in the whole process?
Isn't setting the compile options, hard coding them into the make file, doesn't this go against the philosophy of CMake? Because the compiling options depend on the machine. You may have Isn't it better to put it into a tool chain or?
I agree. I think I would try to. I wanted to show you how you can set them if you need to set them, but I would actually try to avoid setting them at the beginning, because CMake will try to do the right thing. So what I would rather do is not set them, but I would inspect what is CMake pick and try to go with it, because I mean CMake knows a lot about the systems. It will hopefully make good suggestion about the flags, but I wanted to show a way of like overriding it. But very good recommendation, because it makes it a bit less portable, in fact. So we are now 1 hour in. We didn't talk yet about the targets-based build system, but not a problem. We can do that after the break. So I can do that. So after the break, we will restart with target-based build systems, and then we will build it up further, larger dependencies, libraries, etc. So I recommend let's take a 10-minute break, and we will be back 41 minutes past 2. Should I put some timer here, or somebody can? I'll put it on the chat. I'll put it on Zoom chat.
I will put a timer.
Okay. Okay, I will take the screen. So we now did these two parts, the compile flags definition, debugging, that was a bit quick, but we don't have to remember it. I just wanted to know where to find it if you need it. I wanted now to spend some time on explaining this target-based build system, the targets, because I think this is the core of CMake. And it's really cool, and I think it's underrated, and I didn't understand it for a long while. Hopefully I can explain it. Very, very powerful. So I will go in there. And here the goal, let me zoom in, is that in CMake we try to work with targets instead of variables. So instead of having a variable with all the include folders and all the library folders and library names, instead we will work with targets and properties. And then we will see that there are different visibility levels: private, public, interface, and I will actually demonstrate to you what they do. Very, very powerful. And we will build it up, and now we will go a step further, and we will build a project that goes over multiple folders. And how can we handle multiple targets in one project? So targets, we have seen two of them already. We have defined executables and a library. So we had this hello world executable, we had the greeting library. We can even define our own custom targets. And targets have properties. So they can have compile options, compile definitions. They have their own include folders, sources, linked libraries, some other properties. These properties you can set them, but you can also query them with get and set target property. And we will meet some of these commands. Maybe the 5 most used ones are target sources. So we list what are the source code, what are the sources that belong to a target, what are the compile options and definitions, where are the header files and module files, and what to link this library against. And there is more than that, and here there is some, here you can find all the other commands. Properties, they have a scope, and that is very powerful, because when I started writing CMake, I put everything into the global scope. Compile options, compile definitions, include directories. Everything was explicit and in the global scope. And that bit me when the project grew larger. Here we will see that there is a much better way. And we will work with these visibility levels. So when we define properties in a target, like sources or include directories, we can declare them as public or private or interface. And I want to show you an example what that means and how powerful that can be. And the example that I will take is a hello world again. But now things got even more modular. I think it got maybe too modular, because now the person who wrote this split it up into a greeting folder, a hello world folder, even a world folder. So there are more files. And now that we don't have to copy paste so much, you can also go into the, so if you download it or clone the CMake workshop, you can go into content examples. And the example is this, what is it? Property visibility, this one. So I'll go in and demonstrate something. In this case, it's C++, but the same principle applies to Fortran. We have one CMake lists.txt only. later we will maybe find out that we might want to split it up into several, but right now we have one. And maybe let's have a look. C++ project. We define a couple of libraries. So there is the main executable, and the main executable links to the greeting library. The greeting library has a private implementation, but a public interface. The greeting library links to the Hello World library. The Hello World library links to the World library. Here is the World library. So it's a bit, the project is too complex for its purpose. But I wanted to show here how you can nicely separate what is public, what is private. I want to show you what that means really. So we have this a bit too granular project. And I did something else. If you look into these files, for instance, world CPP, I put in this little trick so that I can see this will print a message at compile time, actually at configure time, at compile time, when if this definition is defined. So I can, this is just a trick for me to see whether the code or whether this definition is defined or not. First step I will do is I will build it. Let's do it, make the build. Oh, let's do it more properly, CMake as build. So I configured the code, and let me also build it. And it compiles these different libraries and links them all nicely together. If you have this graph is installed, you can even try to create this graph. This can be nice for more complicated projects.
Did you have to put something into the CMake list file to have the graph list ability?
No. So only thing you need to actually have this installed, but that's it. So it can create this this file project dot, which graph is, and my understanding is that dot is part of the graphis library, which can then create these figures. Okay, this is really tiny. Can I somehow? Actually, I don't know what you see now, but if I, oh yeah, I can somehow zoom in. So, well, this shows me that example depends on greeting, which depends on hello world, which depends on world. So this is just a silly example. But now I want to show you something really cool. And that is, I want to define a compile time definition. I want to define this my definition on the library world. But now I can control how visible should this thing be. If it will be private, it will be only visible to this library. If I make it public, it will be visible here, but also here. And then I can also make it interface. Then it will be invisible here, but it will be visible in the caller. So this can be useful when a library is like an interface to another library, and it just sort of forwards compile definitions. So I want to demonstrate that because that is very, very powerful. And you can use it not only for compile definitions, but also for include folders, library definitions. You can control who will see them. Oops. So here we go. I will, where did I have to do it? In the CMake list. So let me first define it as public. Oh, sorry, as private. And now CMake. CMake. Well, how many typos can I make? And I will call it the build folder. I will call it build private. And now I want to compile the private build private. And from the output, I can see that the world.cpp saw the definition, but everybody else didn't. You could also compile with verbose flags, and then you would see that in the compilation of world.cpp, there was a -d, my definition equals something. But in all the other libraries didn't see it. What happens if I switch it to public? Let's do the same thing again. Public and public. And now the world.cpp sees it and the hello world.cpp sees it. And I could do the same thing with interface, and then I would see that now only this one has the definition. And this visibility, now we can control, this is what it all means. So here I can control the visibility of the include flags. Here I have to have them public. Why? Because this library here will have to be able to read this header file. I can try to make it wrong, but if I set it to private, it will not work, because now it doesn't know where to find this one. So you can really fine tune and control. And I think in reality, actually, I admit that I have never used interface. So I only use private and public, but now we understand what it means. And in practice, what I often do is I make everything private, and then I slowly relax certain interfaces until it compiles, and then I see which ones is public. The other big advantage of this is that I can see which parts of the code are used by other parts of the code. So it makes it more explicit for me to see, like I can go into this and I can modify it, and I know that the only thing that will be affected will be this library. But the public ones, I know that they have effect on other libraries. So this is very, very, very important. So this demonstration I did, yeah, we did that. And please ask away if you have questions about that.
I have a question. So I couldn't really exactly understand what you did by putting the target compile definition. So was it necessary to make it private? Could you make it like public? Would it change the output? Or what's the use of this private? Yeah.
Yeah. Great question. So let me go to the. So this my definition. One way of doing it would be actually I can go in and say add definitions. My definition equals something. That's one way of doing it, but it would mean that all the source files will see it. If you compile with verbose, you will see that on every compile line, there will be a -d definition on every source file. This may or may not be what you want. Sometimes you want to have a bit more fine-grained control. You don't want to affect the entire project. Especially what if I include part of the project is actually fetched from the internet and maybe a completely different library? Then I don't want this definition on my entire project. Here I can, instead, I can set it, and if I define it as private, it will only be, the definition will only be set on this target. So only this source code will see it and this source code will see it. If I set it to public, this one will see it, this one will see it, and also these two. Why? Because this library links to this one.
Okay, I understand.
Mm-hmm.
Yes.
The other thing that is really nice here is that you don't see any explicit folders or file names. So when I link hello world against world, I don't have to specify that it's called libworld.a or libworld.so or libworld.dll or I don't know, dylib. I keep it kind of abstract because I let CMake do the details because the details depend on the machine. So I really avoid here calling explicit file names folders. And this gives me a lot of control.
So I have a follow-up question because I could understand that. So the world.hpp is in the case where the world.hpp is public. So other files include this header. The definition would be propagated to those header files, right?
Yes.
So even if I put it as public, the definition would be visible from other files in the header file via the header file.
If you make it public, it will be visible in this library and in this one.
Yes. Okay. So because the header file of world.hpp will have if-def my definition. Oh, okay, I get it. Okay.
Yeah.
Okay, thanks.
Yeah. So it may seem like not an amazing thing, but this is one of the most amazing things about CMake. I didn't appreciate it for the longest time. So if this was not clear, I encourage you to later to experiment with it. It's good to have a control on this. This is also really important for Fortran as well. And in this next example, so we can exercise a little bit because now there will be something both for C++ and for Fortran, and you will see these visibility levels. And the exercise here will be, let me first explain what you need to do. Now we have a larger project. And this project has a couple of folders. There is even an external folder with some external library, whatever. There is a source folder with a couple of libraries. There is a Fortran version and a C++ version. I just want to show you where you can find it. So in the examples, this is these multiple folders. So your goal in a moment will be you can either take the problem, try to arrive at a solution, or go to the solution and try to make sense of it. So I think both is really good learning. In the problem, there is a Fortran version C++. Let me go to the Fortran one. And here, the goal of this exercise is the following. We have now these files. I will show you in a moment what they do. We don't have to understand the details here, but we have lots of files, but we have only one CMake list. And the goal of this exercise will be so let's look at the definitions here. In the CMake lists, this we already know. We define libraries. So there's one library, another one, another one, another one. Your goal will be to push these libraries further down the directories closer to where the source code is. So instead of one CMake list, we want to have several CMake lists. And we want to, you can use this add subdirectory. So by add subdirectory src, the CMake list will go into src and it will expect a CMake list in there. Notice also in Fortran how this looks super nice here. So in Fortran, you can then, with this private and public, I can already see that these two Fortran files, they generate modules which will be needed by the library linking against evolution. But there is also a source code that produces a module which is not needed outside. So this will nicely isolate the namespaces. And okay, I should also show you what this code does at all.
Why don't you just, why do you separate target sources from add library? Can't you just list the sources in add library with the public and private attribute?
Yeah, this is a good question. Actually, I'm unsure whether, So you don't have to do it in these 2 steps. You can also do add library name and actually list them. This is what we have been doing before. Let me see, add library. Do I have somewhere a link to the help here? Let's see what the help says. What I don't remember anymore is, can we have, I'm unsure. I think, oh, yes, we can. Yes, you're right. So we don't have to do it in 2 steps. We can just say a library name, and then we can also say private public. So you don't have to do it in these 2 steps. I kind of like to define the name, then list what is part of it, then maybe list the include directories. So maybe a matter of taste.
So anything that links to evolution, for example, will also have ancestors as a source file. Is that what it means?
It will be able to see. It will not have ancestor source file, but it will make sure that anything that links against evolution will be compiled after these 2 are compiled, because it will probably want to access the ancestor.mod and the evolution.mod. So already this will make sure that things are compiled in the right order. Let me actually show you what the thing does. It's okay, now I did something with my example. What it does, you can try it out, it's kind of fun. It's where is the binary? Oh, I didn't compile. It creates this binary automata. It's cellular automata. So these are really fun things. You can have a look what they are. So there is a Fortran implementation and a C implementation. So what you want to arrive at is, we want to have one CMake list on top, and then we want to define the targets as close as possible to the source files. And then later we want to discuss why that can be good. And you can pick the one that you like better. There is also a bonus part here. So I encourage that we use the next up to 15 minutes on this. So either try to push the CMake list closer to the sources, or study the solution, collect questions, and then we can talk about it. Especially, you can also have a look at this discussion. So here's this good example and bad example. So we will discuss these 2. And I will mute myself, but I will also do the exercise here.
Can I ask something?
Yes.
So when I look at the output of CMake just in the base in the base version of your problem, I see that it compiles the file conversion once to build the target to build the library, and it builds it a second time to build the target automata. So that means that the source file is added to the executable that links against conversion.
Let's see. It was, which one was it? It was this one, right?
Conversion, yes. That's logical since you add it to the interface.
Right. But it shouldn't build this one again, which it doesn't. Yeah. Because this one was the only one I think which was private. But rebuilding it several times, interestingly. Yes, and this is something because we use the Fortran 90 as an interface.
Isn't there a dependency of evolution against or maybe a dependency of one of the files of automata against empty? A use module, a use empty in one of the files?
No. I think no. Let's see. I already forgot because it's been a while that I created this. Let's see. Oh, there is. No. What's going on here? Not visible. Is this not called? This is never called. Doesn't matter, but how? There's one interesting. So I designed this a couple of years ago, and I was thinking something there, but
yeah, that's why it compiles it. It's here.
Yes, right. So I don't know whether people would like more time. So we have more time. I was thinking 5 minutes more, but of course we don't have to go through all of this. We can also spend time discussing why that could be good or too much work. Would somebody like more time? Like there is no stress at all.
I'm okay.
Is anybody working on this?
May I have one question?
Yeah.
Can you please elaborate a little bit more about the command target include directories? What is it, why it is important?
Here we go, and let's see. The target include directories will So maybe it will be clearer if I show you the other way of doing it. I could do this. And I could say, what this line will do is it will add it will add -I, this folder, it expands it external to the compile line. So it will tell the compiler where are include directories. But again, this one is not the best solution because this will put it for the entire project. And every single source file will be compiled with this. A more fine-grained version is this. So this will also add a -I, this folder, but it will only this library will be compiled with it, and because it's public, the libraries that link to it, but nothing else. So it will sort of a short way of answering would be it will create a -I folder. So that's what it does. It tells where are the include directories needed to build this target.
Oh, I see. Because well, strange thing happened when I tried to solve the problem. I forgot inside my library to add this target include, and the funny thing is the library compiled, but however make main CPP doesn't complain that it doesn't know where the library's HPP file is, the header file. So it looks to me really redundant, because if there is a target source defined and library can be compiled without the target include directories, basically it looks to me everything is there. That's the core of my question. But okay, I can just live with it that it should be like this.
Yeah, so if I understand the comment, which is that why it should be able to actually infer the include directory from this part of the, if this is supposed to be public, then also this part needs to be there. Maybe that was the comment. And they go hand in hand. And to some extent, they look a little bit redundant.
Okay, they looked very redundant to me, but I will live with that. It should be like this. Thank you.
Yeah. Yes. So you could remove that part, but you cannot remove this part. Yeah. In some sense, the Fortran solution looks actually a little bit neater because Fortran doesn't need these header files, but then Fortran works with these module files. So at least like the CMake code looks a bit cleaner on the Fortran side.
I still think it's wrong to put the source file in the public attribute of the library. I don't see what you try to achieve here. I don't understand.
This one?
In the Fortran version, at least, because I don't know C++, so I don't know about this. But
interesting. Okay, let's go there. Let's go into the solution. It's possible that I did something wrong. Let's have a look. So let me try to build it and let's see what we get. So this compiles. Now, what happens if I, for instance, here don't, so you say that this should not be public.
Right.
Okay, let's see what happens. Still works. Yeah. Okay. Interesting. So I think you are onto something there, which will probably also make a less recompilation there. So we don't need that. Or what I'm asking myself, because they need to be then compiled in the right order, but they will be, because what I'm asking myself, I need to verify it, is whether things will be always built in the right order if I don't make it public.
Well, there is a dependency on the libraries, isn't there?
Yes. So that should take care of it. I would like to verify it. I think I will verify it in the break. So the way I would now check it, you are probably right. Probably we don't need that. What I will verify in the break is I will make everything private. And then I will try to compile a couple of times on several cores, just to make sure that, just to check whether there is not something built in the wrong order. Normally the target library should also, it should impose a compilation order.
Yes.
But I'm unsure. I still need to verify it, because like in C++, you could still start compiling different libraries in parallel, and then at link step they should be available. But you cannot do that in Fortran. So I need to verify. But it's very likely that it was unnecessary to be public. I will check that in the break and come back to that. So what was the point of this process of splitting the CMake list into several files? It made the CMake list files a little bit more lightweight. Of course, we created several of them. I like doing this because it can help the developers of the project. Because now when I want to modify this IO library and I'm adding files to it, or I rename them, I only have to edit the file that is close to where things are defined. And I don't really have to understand the rest of the CMake project. So I think it can make maintenance a bit easier. So I like the setup. And then, so we can split, it makes it a bit more manageable. We can split things into several, and then we add directories, and they will be processed recursively. This I wanted to discuss with you. And this is also something you can try later. This comes back to this very, very two-modular hello world problem, where we used targets. And it does look a little bit verbose here. So there is an alternative to it, which is not good, but it looks more compact. It looks kind of neat. I have written quite a lot of CMake code like this, which is still out there in the wild. This will probably still compile on Linux. And here we also define the libraries. Instead of target link libraries, you can add dependencies. So you can tell the CMake that this depends on this, and this depends on this. And then we need to tell the compiler where are the include directories. They are here. And where are the libraries? You can find them here. So when it compiles it, it will put this library into the build folder. This is not a good example. And here are some thoughts. And just for the maybe sake of time, let's have a look at them. So one problem with this is that now this definition, it affects the entire project. This can be okay, maybe it's not okay. Same is for the include directories and the link library settings. Again, it affects the whole project. You will also see is that if you try to reorder these, it may work or may not work. So the order, suddenly now the order is important. And we didn't have to worry so much about the order when we define things close to the target. We have these library names, .a. This will probably not work on Windows. This works on Linux. Also, if I rename the library, or if I change something in the library world, I have to also go to a different place in the CMake list and rename things over here. So suddenly I have to modify things in different places. If I want to now take a target out of the CMake lists and put it in a different place, this became more difficult because now I need to remember to also take other things with me. So maintenance got harder. And also when you move part of the CMake into different CMake lists, the risk is high that you forget some of these definitions there, and they are still there, and some include folders, and then the compiler uses them and you may not be aware. So we really recommend to use this target-based approach. It has more local scope, always better local variables than global variables. So this is a very nice mechanism here. I will come back to this question about the Fortran private public. Let's look at the overview where we are. If I see the time correctly, we should take another break like in 15. So I would like to do, before the break, one more thing. We have now done this part. Let's plan a little bit ahead here. Detecting environment, finding and using dependencies. Which one is more important? You might be able to do both. I will skip some of the part that will maybe not manage everything, not a problem. Let's maybe look at the detecting the environment, because I think you will need it. So CMake has tools to do introspection about the system. Again, there is some help available. So these are the different things that CMake has discovered about my system right now. We of course always try to write code that is portable. So we try to minimize things like this, like if this is Windows, if we are on Linux, if this is Mac, if we are on a 64-bit machine, if this library available or that library available. We try to avoid this for portability, but sometimes we have to. So depending on the system, depending on the environment, we may need to compile different portions of the code. So here's an example where we, depending on which operating system, we send a different greeting. And here is one way of doing it. So we can define compile definitions depending on, so CMake knows, for instance, the system name, whether this is Linux or Darwin, macOS, or whether this is Windows. So here's one way of discovering the operating system. We can also query the processor capabilities and generate a configuration file. And here
is Darwin the generic name for macOS, or is it a specific version of macOS?
I think for historical reasons. So I think there is also variable. You can check for macOS, but I think for historical reasons, this is Darwin will now include any macOS on CMake. So I'm in my CMake code, I check for Darwin if I want to know whether this is Mac. But it could be interesting. Those of you who have a Mac, print this variable. Have a look what it contains. And here you can also get information from the CMake host system information function, which can tell you lots of things, like how many physical cores, logical cores. Sometimes you need to compile the code depending on really the architecture, whether it can do all these processor capabilities. Do we have SSE2, MMX? Yeah, so these things we can query. And here's an example. And maybe I will make that part as a demo. And where do we find it? It's in the examples and OS dependent maybe. No, that's the simpler one. How did I place it? Oh, it's the configure file. Here we go. And maybe we can have a look at the solution. So in this example, I want to know, in my code, I want to know a couple of things about the processor. I want to know also actually the compiler and the compiler version, because this will be really nice to have in the output for reproducibility. And one way of doing this is to read it from a config.h file, which doesn't exist yet. But I have this config template.h. And this template.h, it's something that I generate. And I ask now CMake to go in and please replace everything that is between these add. Please replace this by the number of logical cores, physical cores, and here put the CMake, the CXX compiler vendor and the version. And the command that does it is configure file. So configure file is useful because we can generate config.h from a template, and I tell CMake to only replace everything between the adds. This will be then placed in a binary in the build folder, which I need to tell the example code where to find it, because it will include it. Here I'm using this function CMake host information to query a couple of things. And we also see that in CMake we can do a loop. I can loop over some items and do something instead of typing this 8 times. Let me try it out. I have used this function that I mentioned earlier, that CMake print variables, to print them on the fly, just for debugging purposes. And now I generated this config.h. So in my case, 12 logical, 6 physical, and this is what it detected. And now when I build this and run it, this stuff will end up in my output. Take home message here, there was a lot going on. Take home is that there are functions available to discover the system, discover information about the processor. And then there are many ways to get that into the code, but what I like to use is this configure file, which generates a header file based on a template. And in that template, you can let it expand built-in variables, but also here I define my own. And earlier this morning I showed this git hash, and I used the same mechanism there. So what else what else can be really useful to record? So code version and git hash, because then if I find an output, it's nice to know what version did it refer to. Compiler versions, this can be good for debugging. Then if users send you an email that this doesn't work, you can ask them, well, which compiler and which flags, and you see that even in the output. So you can just ask them, please send me the output. Other things that I like to record into the binary is compile time definitions, library versions, maybe some environment variables, just to make the debugging and reproducibility easier.
So if your login node, do you hear me?
Yes.
So if your login node has a different number of cores, for example, than your compute node, how would you do with this? Would you then just run CMake on the compute nodes to get the values right?
Yeah, that's a great
it's
point.
Basically a cross-compile issue.
Yeah. Okay, so you can also cross-compile even to a completely different processor, and it's a bit out of scope, but it can be done. But what I would do in this case is I would configure and compile on the compute node. I like to do that anyhow because then I script the configuration and compilation, and then at least I have it documented. So if I come back to it a year later, I can find out how did I even build it. So I would write a run script that will queue it to the queuing system, and then on the compute node, I will configure and compile. So that's how I would do it.
Yeah, okay, thanks.
Super. So let's have a look here. I think just looking at the time, we should take another break. And after the break, I think I will do two things. We will skip this fetch content, but it's there. I mean, you can try it out. But after the break, I will try to. We should be able to detect and link libraries because that's very important. We need to do that all the time. And also we will have a look at testing in CMake, and then this discussion. So I will skip the fetch content stuff. Before I continue, I wanted to come back to the suggestion, which is, I think, Lionel, about Fortran and private public. So what I did is I tested this to set everything to private, and actually it got better. It got better and better because it does work, but also there is less recompilation because it doesn't compile things multiple times. So I think this is better. So thanks for the suggestion. So either I misunderstood this for many years, or things have changed, and it was maybe needed at some point and not needed anymore. But so this is an improvement. I will improve the material. Thanks for that. So in the Fortran, we don't even have to worry about that. So things get even more compact and even easier. We could have just put everything into the add library. There is a compilation order, but the compilation order is still intact because of the library dependency. So thanks for the suggestion. So my plan for the remaining 45 minutes is that we have a look at libraries and we have a look at C-test and hopefully some discussion. If ever I should run out of time and we don't have time for this discussion, this can also be consumed in reading, because here I write like why listing sources and not globbing them, how to do flow control, how to organize large files, should we use variables or targets, functions or macros, or where to list the sources. So I think the last part could even be done just in reading. And there is a raised hand. Manu. Maybe that's from before, maybe. Or audio.
Okay, sorry.
Yeah.
Do you hear?
Yes, no.
Okay. My question was, what happens if you use make -g to compile? You compile a lot of things parallel, and can it break anything from what you have done with CMake?
Yeah, great question. So you can run on as many cores as there are. It will run the independent tasks in parallel. So this can speed up compilation a lot. It's also very interesting for testing. So then later we will see that we can do C-test -J12 or how many there are. if you see that it breaks, it's not the fault of CMake, but it means that we didn't really tell CMake all the truth. So sometimes you see that, okay, something depends on something that didn't get compiled, but then I probably forgot to express this dependency. But normally, if I do things correctly, it will create a correct makefile that will work even on, I don't know, 128 cores. Okay. So most of the time this works, but if it doesn't, it means that I made a mistake. Then CMake just doesn't know that it should wait for, it doesn't see the relations. Okay, let me go back here to the overview.
Okay, thank you.
Where we are, here we are. So I wanted to go into these libraries, dependencies and ctests. So let's look at dependencies. In CMake, there are a couple of ways to detect, like often we need to find something on this. Is there a library? Is there a library called NumGrid that we can link to, or XCFun, or OpenMP, or NPI, or BLAS, or PAPI, or something? So it has these ways of finding programs, paths, packages, libraries, files. Most of the time, we will use find package. And find package, we can ask for a certain package name. We can ask for a certain version. We can say whether it should be exact version or not. We can ask it to detect it quietly or verbosely. We can even say that this is a required package, so it should actually stop and fail if it cannot find it. And yes. So when we use this find package command, it will actually use a module called find package name.cmake. Many of these are part of the sort of standard library, and I browsed them earlier. So if this link here will list all the ones that are shipped together with CMake. But there are many written by other people. So third party, you can even write your own. It's not part of this workshop now. Let's maybe have a look at find OpenMP. So if I want to know a link to OpenMP, what do I need to do? I can, so there is a lot of info here. What I recommend to do when you can read this online or here in the terminal, what I recommend to do is to look for the imported targets. This is most of the time they are there. This is the thing you want to link against. In this case, the imported targets will be called OpenMP, : OpenMP _ language, for instance, Fortran or CXX. And then I can link against this. And if you do that, you don't have to worry at all about compile flags, definitions, because it will set up the right thing. So this is what you want to go for. It will also define these variables, OpenMP, CXX flags, but you don't have to use them. It's better to do it through these imported targets, and I will actually show you. We will try that out. So if I want to see what is actually available, I can do this. Oops, that was wrong. So they are already there. There might be something that is not here, but then I often look at GitHub. What did people write? Of course, if it's in a compatible license, and we can test it out. And here I have examples for OpenMP, C++. It's again a hello world where we say hello from a certain thread, the Fortran version. And notice how we detect it and how we link to it. So I have my example source file. And here I ask find package, please find me OpenMP on the system. Is it available? It will use this find openmp.cmake, which is part of the CMake distribution. In this case, I require it. It should actually stop if it's not there. And in this case, I'm only interested in the C++ component. And then I link my target against this imported target. And that's it, that's all. Very similar. So in the Fortran, everything is the same, except things change from CXX to Fortran. Same way for MPI. So here's an MPI example. And what I encourage you to do is to now try it out. Take one of the four that is close to what you work with and try to build it. Of course, you may or may not have MPI on your computer. So in this case, maybe easier to go for the OpenMP. But also here the same, we don't have to deal with, I don't have to see the compile flags, I don't have to see any of the stuff. We just import, we link against the target, and it will propagate the flags and definitions to my target. Here, MPI Fortran. As a bonus, if you want, so the goal would be take one of these, browse the documentation for find, I don't know, mpi.cmake. Try to build it. Bonus is for now or later in the week, try to do the same thing with Bast or Lapak or some other library. Also try to build with verbosity and see how it set the right flags for me.
I have a question. When you do this with the MPI, CMake doesn't use the compiler wrapper for MPI, and it just uses options and links to the libraries. This seems to go against the recommendations that you find on supercomputing centers. Have you found this to be a problem?
So if I understand correctly, I forgot to say it here, but in the MPI, you actually may want to do this. Where was this? In this section, you may want to send the compiler here. I probably want to set that this is MPI F90, just to pick up the right wrapper. So that's what I do. So when I build MPI, then with CMake, I set here the wrapper that I wanted to use.
But then if you have a mixture of sequential and parallel executables in your project, it's going to use the wrapper for the sequential code too.
Right. That's right, and that's what so in one project we how do we do that? We do that, we actually compile the code with the wrapper, but we allow it to run also in sequential. In my experience, that works, and that's that's just one project.
So I've seen this also quite frequently. So this works so that you use CC equals MPI wrapper and build also the serial stuff with MPI compiler. But this is a headache for performance tools. So because there we decide on the compiler or the wrapper which libraries we then link. So this works in the CMake case, but creates some issues somewhere else. So, but this is the way usually the people do it. Yeah. So
it's good to know. Very good to know. Interesting to know that this may trouble for other people.
In the philosophy of CMake, it seems to be better to let FC equal to the compiler without the wrapper and do, as you said, link to MPI, and then if you just do what it needs.
And I think it should work. So let me try it out. will take the MPI one because I have MPI on this system here. I think it will work without me setting any compiler. Here we go, MPI, I don't know, C++. Actually, I can go because I have this example. In the examples, it was in find package, MPI. And in here, it's exactly this example. And now I will not do anything. I will just create a folder, configure. Let's see what it will detect. So it detected MPI. Let's build. Looks all right. But now if I do, let me try this. Boom, bach. And I think this is interesting. Okay, I don't have so many. So I think it seems to work.
Yeah, if you compile with verbose, you can see that it doesn't use the wrapper, it just links to the library.
So let's see what it took. It here. Yes, it doesn't compile it with the wrapper.
But this is a general question, a philosophical problem. When we use a build system like this, does it still make sense to use the wrappers provided by the systems? Because the wrappers are the combination of calling the compiler with some options. And with these build system tools, you're supposed to give the compiler and the options, and the system is supposed to find them for you. So I would expect that you shouldn't use the wrappers when you use the a tool like CMake or Autotools, but it's not clear to me if we should or not use the wrappers in the end.
Yeah.
Because it's the same problem with HDF5. HDF5 has its own wrapper to compile, and so if you want to combine MPI and HDF5, do you take the wrapper from HDF5 or MPI? Or do you use some combination of both? So at the end, it makes the complexity somewhere else.
Yeah. Yeah, so I don't have a good answer, but I can just say what I did until this moment is that I never thought about it too deeply. I've always specified the wrapper from outside. That's what I did, but today I learned that this makes actually trouble for other people in other contexts. In production, I have actually never tried this, what I did right now, not specifying the wrapper. I've never tried it.
Because you can also expect when you use the wrapper that some libraries will be used multiple times.
So in our performance tools, we face the same problem. So we have several libraries that are serial, and then some parallel stuff, and we need to link them together at a later stage. So we basically have not only one configure run, but we have one configure run for the serial parts and one for the MPI parts. And we have a top level configure that orchestrates this stuff. So from the top level, we call two other configures and pass the correct compiler or compiler wrappers into this file. So this is quite complicated, but this works. And I think you could do a similar thing with CMake by wrapping two CMake invocations with a script, or I'm not sure if this is possible within CMake itself.
Yeah, so you can, what one would probably, the proper way would have been in this case to define two different executables. One would be sequential, one would be parallel. And CMake can invoke also CMake itself. So one can do that too.
that doesn't seem necessary here. It's not if you just don't choose the wrapper. I see from the documentation of CMake I'm looking at right now that CMake attempts to find an MPI compiler wrapper and determine the compiler information from it. So CMake analyzes the wrapper, it seems.
Mm-hmm. Yeah. Great questions. I don't really have a very good answer there. Before moving on to the testing, would somebody like more time here? Any questions about linking? Did anybody try the OpenMP? Did it work?
So can I ask a question related to this? So I'm trying to do exactly what you showed here for my library on a cluster. And unfortunately, there is no CMake module, for example, for StarPU, which is one of the libraries that I use. But it has a pkg config, so .pc file. And you mentioned that one could also use pkg config with CMake.
Yes.
Right? Is that?
Yeah, I'm just taking a note here. So I will put on the Slack later some link to resource on how to do that. Yes. And that was OBJ, right?
Yes, yeah.
Yeah, great. So thanks for the question. I will share later. So I didn't want to put pkg config here for several reasons. It's for the sake of time, but it's also something that kind of binds it to Linux. But actually, very often we are on a Unix-like system. So it's, for many codes, this is completely okay. All right, so we have like 20 minutes left. Maybe we can have a look at the next episode, which is testing. And that will be it. So there is this fetch content, but it will be just as a read-only episode. And I think it's nice to know about ctest. So ctest is CMake actually comes with a couple of packages. It's not only CMake, it's also cpack for packaging, ctest for testing. I think it's nice to know about this, even if you use your own favorite set testing library. It can be still nice if there is ctest around it. And at least for two reasons. One reason is that people often don't want to, they don't want to read the documentation of my code. They just want to configure, build, test, install. And then it's nice if I can provide like a standard way of doing it. So configure, make, test, make, install, and we can implement that with CMake. So it can just provide a standard interface to the user, or to easy builds back. Then people writing easy build configs, they don't have to go into my code to figure out how to test it. The other thing that I really like about ctest, it has all the flexibility. I mean, you can do everything, but what I really like is that I can run again my test in parallel. That I find very, very beneficial. It just speeds up testing, and speeding up testing actually makes sure that we actually run the tests. So that can be, it's just good for everybody. So I will not show everything that ctest can do, but just a few things. And we need to do only two commands. One is enable testing. Oh, this one is not linked correctly. I need to link that. Enable testing, and the other one is add test. And in the add test, there are two things we have to do, and the rest is optional. And the two things we have to do is we give it a name, and we tell it what to do. And the command can be really anything. It can be a Google test, it can be a shell script, it can be a Python script, it can be something home written. The only thing that is interesting to CMake is whether it returns 0 or non-zero. 0 success, non-zero failed, but can be really anything. And then if you look at the test documentation, there is really a lot one can do, especially Do we have properties here? Oh, it will be linked somewhere else. We can define test properties. I will come back to that. So here I have an example, and you can type along. So this will be in this example testing. Let's go out of this. And here it's a C++ code where let me build it just to show you what it does. It's a silly code that can sum up command line arguments. So in this case, 1 + 2 + 3 + 4 + 5 is 15, or 200 + 300 is 500. So it's a silly code. It uses this function that I want to now unit test. There is this function which gets a vector of integers and it returns its sum. And I want to unit test it, and I have written a test for it. And this is now not, I'm not using any test library. This is then, you can have a look at in the fetch content where I'm using catch2. In the intro this morning, I was using Google test. In Fortran, there is this PF unit. So you could use some test library test framework instead. Here I'm doing it in a really pedestrian way. So I wrote this executable, which will call the function. It will verify that in this case, sum of this is 15. And if yes, it returns 0. And if not, it returns 1. Instead of this, it could be a Python script. And let us inspect how the CMake lists look. The interesting part is this part over down here. So we have enabled testing, which will enable the C-test machinery. And then I can define my tests. In this case, I have only one test. I can give it a name, and you can have several tests. And then later I will show you, you can add the labels. And this is kind of neat, which I didn't mention what that is. So instead of, so where is my test? My test is an executable. And it's called CVP test, and it lands somewhere in the binary directory. Here I could say, instead of this, I could say project binary dir CVP test, something like this. It would also work. This one, this is using so-called generate expression, and there is a link where you can read more. Generator expressions. They are really nice in CMake because I can refer to this file without referring to its path and file name, because the file name could change depending on the operating system, and also the path could. I don't really need to know. So it's a more general way of calling it. And that's it. So if I build, then now I can run ctest. And ctest runs this one test. And you can also run with verbosity. And actually I can do make test, which will run ctest. Make test. Yeah. So we have a test target. And this is still very simple, but now I can define lots of properties on the test. Let's have a look what we can define. Set test properties. Well, it doesn't really here see properties here. I can make tests depend on other tests, labels, timeouts. If I expect something to fail, I can tell it to CMake that it will fail. Maybe the last thing I wanted to show today is the cost, which is kind of interesting. So I want to show you how we can define the property cost and what it means. Oh yeah, there is a full command line interface to ctest. Oh, I think what is nice is like stop on failure, output on failure. It can do lots of things. But I wanted to show you this other example, which is yeah, so this is good to know. I can run them in parallel, like this or like this, so this is great. In this case, I have only one test, so it's a bit boring to run it in parallel. But I will now show you an example where we see the cost property and how can that be really good for your code. Where do I find it? I find it in testing parallel. So let me show you how to run testing parallel. Testing parallel. And the CMake lists, what do we have here? This is a project with the language none because there is no compilation happening. I'm just running some Python scripts. So it's running, I'm detecting Python. And this find package will define this Python executable for me. This is better than writing Python here because Python could be Python or Python 3. This will do the writing. And then I have a couple of tests and they have a label. Sorry, they have a name, A, B, C, D until I. And they write some Python, then run some Python codes. And I want to show you how that looks. These Python tests, all they do is that I'm simulating that this takes a little bit of time. So these tests take like a second or two, and they take different duration. Let me configure. There is nothing to be compiled here, but I can run the test. And now what I want you to look at is it will now run the tests one after another. I also want you to look at in which order will it run it. So it runs them A, B, C, D, E, F, G. It runs them in the order as they are defined. These tests have different length. So some of them take half a second, some of them take 1.5 seconds. The last one takes 4.5 seconds. So my point in this exercise is that I have defined these tests this way and they will be run this way. I could run them also parallel and they will still be run this way. But now it can be useful for me to actually define the cost property. And I will do that. And what I now tell CMake is the cost is a unitless number, which will tell CMake how costly are they. So I could either reorder them, but I could also give them a cost, which is how long do they run. And now what we will see is that if I run it again, it will actually start with the most costly one. Ctest. Let me reconfigure ctest. It will start with the longest one. And that is maybe not so interesting now when I run them one after another. But it can be really good if I run them in parallel. So I can now run it ctest -j for, let's do it on 4 cores. Because then it will start with the slowest, with the longest, and it will backfill then as soon as my processes become available, it will schedule a shorter one. And the overall time now is less than if I run them in the other order. So take home from this is that I can run test in parallel. This is very nice. And the order can be, it can be useful to actually start with the slowest if you run them in parallel. And there is a way to tell this to CMake. And there are lots of other options. So any custom command can be defined as a test in CMake. You can then run them through ctest, which will also create a make test target. And ctest has all these command line options, but it particularly shines when running test in parallel. Of course, it's a little bit up to the project whether you want to run things like through your test runner or through ctest, because also your test runner may have all these command line interfaces. And one example that I invite you to check out later, but I will not have time today, is to have a look at this fetch content. And I show an example with catch2, which is another testing library in C++. And then there is the question, should we have it run as one CMake test or several CMake tests? What you can also try is to fetch pfunit, compile pfunit, link pfunit, and run your test set in Fortran through pfunit or similar libraries. So we have 10 minutes left. Do you have questions about testing? Or any other topic? Otherwise, I would go to this summary here. Oh yeah, there is a question or a comment. Otto, yes. Or is that from earlier and I missed it?
I have a question. So we have also a project where we do testing for the distribution. So we have a distributed version of our library, and then for the distributed version, we do a test to check that the distribution has the correct files. So this CMake, how would we handle that? For example, make a like a tarball, and then check that the tests that we include in the tarball are okay. I mean,
this is source distribution or just like binaries?
No, the source distribution, yes.
Yeah. I think what I would do is in like GitHub Actions or I don't know, GitLab CI or any of the continuous integration nightly tests, I would let it download the release tarball, extract it, configure it, compile it, test it, install it. So I would do that. I would test this outside of CMake in a sense.
Okay. Yes.
If I got the question.
Yeah. Yes.
Yeah.
Yes.
So I would not. One could probably let. Like one could let CMake do all of this as well, but I would just keep it. Like the idea is that the user will interact with the configuration and compilation the same way the developer, but might see a subset because they will just see a subset of tests and only the release branch, release version, but they interact with it the same way. And of course, then you let some automated testing do it for you. And the advantage is that it keeps the CMake a little bit more simple. And also the other advantage is that the developer is doing the same thing that the user will do, which means that we detect problems earlier while working on them instead of doing something very different.
Okay. Okay. So is there an equivalent command like make this check for CMake or?
Good. I don't know. Okay. I never tried, but please let me know if you find out. I will also have a look.
Okay. Thanks.
This check was really nice.
So make this check generates a tarball. So and does some various checks before it says the tarball is okay for distributing. I think you mentioned that there is this CPEG program or component that can be used to create tarballs. So maybe you should look into this CPAC for generating a tarball.
Yeah. So I have used CPAC. What I haven't done is done anything testing together with CPAC. So I do CPAC at the very end, but then testing of the CPAC archive I've only done by an automated testing pipeline. That would be interesting to know whether this can be really incorporated into the process. So in other words, I have only detected degradations after it has been packaged by automated testing. But maybe you want to know that before. So I don't know whether Otto's question is still relevant.
Can you hear me now?
Yes.
Yeah, sorry, I had some problems with my microphone. Well, basically, I have just a short question about, as you remember, when I was talking about Turbo RVB, I had this idea that I would like to try which files can be compiled at which level of optimization. And according to our experience, this has to be tried by different, because different compilers can achieve different parts to different optimization level. So, and my question is, can I use these tests during the compile time as a compile time test, or there should be only used as a check if everything's okay? You know what I mean?
Yeah. Yes. So what you want to do is you want to do something like, so there is something called try compile where you can attempt compilation.
Yes.
Exactly. But actually, in your case, it will compile. But what you want to know is whether it runs correctly. I would not do that with C-test, because C-test for me happens after we have built. It's a different step. But you can, and I will find some pointers, and I made some note here that I will share it on Slack, is that you can probe compilation, and you can also run custom commands at configure or build time. Maybe in your case, what you want to do is at configure time, you want to compile an example code and run it, and then you can run any script. So you would define your own script that actually runs it and verifies. So you would write your own script that runs an executable and checks the output, and then based on the result, it would report back to CMake whether it should switch on some compile flags or not.
So here you need to be aware that the login node architecture might differ from the compute node architecture. So we usually try to avoid running programs at configure time, but you can also get a lot of information by linking. So and so some of the Autotools macros are quite sophisticated in finding out some information just by compiling several times. So this is really weird stuff, but this avoids running programs on the login nodes that might differ from the compute nodes.
Yes, very good point. And again, one could solve it by scheduling also the configuration to the compute node, but there is risk that somebody will forget that, and then you get a different result. So this probing compilation, very often, as you said, you don't need it, because this fine package, they are very good at figuring it out. But I don't think there is any, like in your particular case, so in Otto's case, that there are a couple of source files that actually generate objects which yield a wrong result. This will be, I think for this you need to write a custom script that is run at configure time, but with all the risk attached here.
Okay.
So it can be done. I will share some pointers on how to do it.
Okay, thank you. Okay, just as a side note, there is one inconvenient thing is some of these objects are generated via taking as an algorithm differentiation and are very long source files. So it even happened that one aggressive compilation of these files can took 40 minutes or something of one file. So this is another thing one has to take to account, that one doesn't want to have a configure that takes, I don't know how long time. So and this is actually one of the reasons why on some machine we had to always run it on the compute node, because it doesn't have the limits for the it was too long to run the executable for on the login node for so long. So
yeah,
okay, but thank you very much.
I see the problem. It's non-trivial. I think I would, in this case, probably try to find out why it's miscompiled, but I also understand why it can be very difficult to find it out, especially if this is automatically differentiated code. Was there any other comment? I saw a hand. Lionel?
Yes, I missed something that you said. Did you say that you can run several tests together? So how does this work? Do you catch what return code do you catch then?
So it will.
I mean,
it will. If the tests itself are sequential executables, then it will. C-test will see which tests are independent, and by default, all of them are completely independent, and it will run them in parallel, one after another. Some tests may be dependent, but then you can tell it to CMake that this test depends on the output of the other tests, so please don't run them at the same time, and then it will schedule it. So it's a bit like a make that can parallelize a workflow. So that was meant, if that was a good answer, or I hope I answered the question actually.
Okay, I thought you said that, maybe I didn't understand. I thought you said that one executable runs several tests. But maybe I got it wrong.
No, that's okay. Just really quick screenshot. I understand we are almost out of time, so this will not take long. I just want to. Where do we have that? Here in. Okay, so let me show you here. In the fetch content, I could define a couple of tests here. For instance, short, some labels, some tags. So now I have two CMake tests, and they can be run at the same time. But I can also, the other option that I have is that I just run this binary. So then from CMake perspective, it's just one test. But inside the binary, there are actually several tests. But there, of course, CMake doesn't have any control, so they will be run, it will just run this file. So my point of this was to, so we didn't have time to talk about it, but what I find actually useful is in test frameworks like Catch, Google Test, I can define these tags, and then I find it actually useful to have them appear as two tests also in CMake, because then I can run them in parallel instead of just running all of them one after another. Of course, it doesn't matter if everything takes a couple of seconds, but it will matter if it takes 2 hours. All right, so I think my time is up. But it was a long day. Thanks so much for listening, and thanks for the great suggestions. I took a couple of notes of things I need to follow up on and find out. I will share on Slack. And
thank you
forward to. Yep.
I would like to thank you for all the work you did for this day. Yeah. And I would like also to tell to all the participants that for tomorrow, for the Autotools tutorial, it will work in the same way with a web page, and so you will have to set up a Conda environment just like you did for today, and the instructions are on the Slack.